How does a home die? Not just a house, not just a city, but a home that spans billions of kilometers, a home that has cradled life for nearly 4.5 billion years. How does the solar system, this delicate clockwork of planets, moons, and asteroids, this tiny island of light in an ocean of darkness, finally come undone? It's a question that feels almost impossible to ask, because from where we stand, everything feels so permanent. The sun rises, reliable and warm. The planets trace their ancient paths across the sky, unchanging. We build our lives, our civilizations, our memories on the assumption that tomorrow will be like today. But here's the uncomfortable truth that every astronomer knows. Nothing lasts forever. The universe is a place of constant change, of slow decay, of inevitable endings. And our solar system, for all its majesty, is not immune. I'm Christopher, and this is Space. Today, we're going to stare that uncomfortable truth in the face. We're going to explore every way, from the certain to the wildly improbable, that our cosmic neighborhood can meet its end. But before we get to the fire and the ice, before we talk about stars going supernova or rogue planets crashing the party, we need to set the stage. We need to understand the tension at the heart of this story. On one hand, you have the sun, a ball of nuclear fire that has faithfully fueled our world for billions of years. It feels everlasting, doesn't it? A constant, unchanging anchor. On the other hand, we know the sun is a star, and like every star that has ever existed, it has a life cycle. It was born from a collapsing cloud of gas and dust. It is living its middle age right now, and one day, far, far in the future, it will die. That is not a possibility. That is a certainty. And that certainty is just the beginning. Because the end of the solar system isn't just about the sun running out of fuel. That's the headline. But the full story is far more terrifying, far more fascinating, and far more complex. Think about it. The solar system is a dynamic, chaotic place. It's not a perfect machine. It's a swirling river of gravity and motion, where every single object pulls on every other object, creating tiny nudges that can build up over millions of years. A passing star could drift too close, tearing planets from their orbits and flinging them into the void. A supernova from a distant, dying giant could blast us with radiation so intense it strips our atmosphere clean. There are even scenarios, subtle and slow, where the planets slowly destabilize each other, a gentle gravitational dance that eventually turns into a brutal shoving match, sending worlds crashing into the sun, or careening out into interstellar space. So what are we really talking about? We're talking about 4 major categories of destruction. First, the inevitable, the evolution of the sun itself. From its gradual brightening over the next billion years, boiling our oceans away, to its dramatic transformation into a red giant, swelling past the orbit of Earth and consuming everything in its path. That is the slow, patient death. Second, the chaotic, gravitational encounters. This includes the tiny, cumulative chaos of planetary orbits, but also the terrifying possibility of a rogue star or a rogue planet wandering through our neighborhood. Third, the violent, high-energy astrophysical events. A gamma ray burst from a nearby star, a supernova shock wave, even the quiet but deadly threat of a white dwarf or neutron star drifting through. And finally, the long game, slow orbital chaos, the idea that over billions of years, the solar system is not a stable system at all, but a chaotic one, where tiny changes snowball into cataclysmic reshuffling. Each one of these paths leads to the same place, an end. A final state where the sun is cold and dark, where the planets are either vaporized, ejected, or frozen in a silent graveyard. A solar system that is nothing but drifting debris and the faint, dying light of a white dwarf, a ghost star too dim to illuminate anything. It's a haunting image, isn't it? To stand here in the warmth of the sun, feeling the breeze on your face, and imagine a future where all of this is gone. Where Earth is nothing but rock orbiting a cinder, or maybe nothing at all. Where the vibrant disk of planets we know so well has been scattered across the galaxy like ash on the wind. But here's the thing about these endings. Some are almost certain. Others are so improbable they might never happen. But the beauty of astronomy, the reason we look up at the night sky with wonder, is that we can imagine them all. We can run the simulations. We can trace the gravitational threads into the deep future. We can ask the terrifying, beautiful question, what happens next? And we can answer it, piece by piece, scenario by scenario, from the utterly predictable to the fantastically unlikely. So before we walk through the fire, before we watch our sun wither and die, before we see planets thrown into darkness or blasted by cosmic rays, let's just sit with that question for a moment. Imagine a future not in a few decades or a few centuries, but in a few billion years. Imagine that the light you see right now is the last true sunlight. Imagine a sky where the familiar constellations are gone, not because the stars moved, but because the Earth isn't here to see them anymore. Imagine the silence, and then ask yourself, is that the end of the story? Or is it just the beginning of something else out there, in the cold, dark spaces between the stars? We're about to find out. Stay with me. Here it is, the thing we all know is coming. The one ending we can set our watches to. For all the cosmic chaos we've talked about, rogue planets, wandering black holes, stray gamma-ray bursts, there is one end that is absolutely, positively, mathematically certain. It's the baseline, the default setting, the universe's way of saying, don't worry, I've got a plan for this one. We're talking about the death of the sun. And when that happens, everything changes. Everything we know, everything we've ever loved, every beach you've ever walked on, every song you've ever hummed, every photograph of a birthday party, all of it, gone, not because something hit us, not because some external monster snuck up from the dark, but because our own star, the very engine of life, will eventually run out of fuel. But here's the thing. It's not like a candle flickering out at a party. It's violent, it's beautiful, it's slow, painfully slow, and it's going to take billions of years to play out. But it starts right now. In fact, it started a long time ago. It's already happening. You just can't feel it yet. Right now, the sun is in its middle age. It's about 4.6 billion years old. That sounds ancient, and it is, but in stellar terms, it's basically a 40-year-old human with a steady job and a mortgage. It's stable, comfortable. The sun is burning hydrogen in its core, fusing it into helium, and that reaction releases the energy that lights up our entire solar system. It's been doing this for billions of years, and it will keep doing it for about another 5 billion years. But here's the catch. It's not just burning hydrogen. It's leaving something behind. Every time two hydrogen atoms smash together to make helium, a tiny little leftover sits there in the core. Helium, inert, lazy, useless helium. It doesn't burn like hydrogen. It just accumulates like dirty laundry piling up in the corner of a teenager's room. And over geologic time, that pile gets bigger and bigger and bigger. Right now, the sun's core is about 70% helium. That's a lot of ash. And as that ash builds up, the core gets denser, heavier. Gravity starts to pull it inward, squeezing it tighter. And here's where it gets interesting. When you squeeze something, it gets hot. So the core is slowly heating up because it's being compressed by its own weight. And as it gets hotter, the hydrogen fusion rate increases. The sun gets brighter. A little bit brighter every year. Just a tiny amount. You wouldn't notice it in a human lifetime, but over 100 million years? That adds up. In about 1 billion years from now, that increased brightness will be enough to boil the oceans. Not the red giant phase, not the dramatic expansion, just the slow, relentless march of a star getting hotter. Earth will start to look like Venus. The atmosphere will strip away. The water will evaporate into space. Life as we know it will be gone. No more trees. No more animals. No more anything alive on the surface. The planet will become a scorched, barren rock. And that's still 4 billion years before the sun even turns into a red giant. So let that sink in. The end of life on Earth happens way before the end of the sun. We're not going to see the fireworks. We're going to be dead long before the main event. But let's keep going, because the sun isn't done. It keeps burning. It keeps building up that helium ash. And after about 5 billion more years, something critical happens. The core becomes so dense and so hot that it can't take it anymore. The pressure is immense. The temperature in the core reaches about 100 million degrees. But here's the problem. Helium doesn't want to fuse at those temperatures. It's stubborn. It takes even more heat, even more pressure, to get helium to do anything useful. So the core contracts further, it gets smaller, hotter, denser, and eventually the sun's core runs out of hydrogen to burn. That's it. The fuel tank is empty. And when that happens, the core starts to collapse under its own weight. Now, this is where the whole thing goes sideways. When the core collapses, it releases a massive amount of gravitational energy. That energy heats up a shell of hydrogen surrounding the core, and that shell, that thin layer of leftover hydrogen, suddenly ignites. It starts fusing into helium, and this shell burning is a game changer. It's violent, it's unstable, and it pushes the outer layers of the sun outward. Imagine blowing up a balloon. The shell burning is like a hot internal wind, inflating the star from the inside out. The sun starts to swell, slowly at first, then faster. It begins to leave the main sequence. It becomes what astronomers call a red giant. And when I say swell, I mean swell. The sun's radius expands to about 100 times its current size, maybe even 200 times. The surface cools down. That's why it's red. But the sheer size of the thing makes it incredibly bright. We're talking hundreds, maybe thousands of times the sun's current luminosity. It's not a spot of light in the sky anymore. It's a giant, looming orb that fills half the horizon. Mercury doesn't stand a chance. It's the closest planet and it gets swallowed first, vaporized, turned into a cloud of atoms that gets scattered into the solar wind. Venus is next. It goes the same way. The atmosphere, the surface, the entire planet. Gone, obliterated, nothing left but a faint memory in the plasma of the giant star. And Earth? Well, this is the big question. The one that keeps astronomers up at night. Will Earth be engulfed or just boiled away from the outside? The answer is complicated. It depends on exactly how large the sun gets, and exactly how much mass it loses along the way. Remember, as the sun expands, it also loses mass. A red giant star sheds its outer layers into space. That mass loss weakens the gravitational pull on the planets. So the planets start to drift outward. Their orbits expand. It's a cosmic game of tug-of-war, and the sun is slowly letting go. Most models suggest that Earth will probably be engulfed. The sun's radius will expand to about 1 astronomical unit, the distance from the Earth to the sun. That's right. The sun will basically grow to touch our orbit, and even if it doesn't quite reach us, the tidal forces, the drag from the outer atmosphere, the sheer heat, Earth will spiral inward and be vaporized. It's an almost certain death sentence. But let's say Earth somehow survives that, on the outermost edge of the red giant's atmosphere. Even then, the planet is doomed. The surface temperature will be thousands of degrees. The rocks will melt. The oceans are already long gone. There is no scenario where Earth remains a solid intact planet after the sun becomes a red giant. Earth is gone, Mars survives, at least it survives the first wave. It gets pushed outward too. The asteroid belt gets pushed outward. The gas giants feel the shift. Jupiter, Saturn, Uranus, Neptune. They all drift to wider orbits as the sun sheds mass. It's a slow dance of planets moving away from a dying star. But they survive. For now. The red giant phase lasts about 700 million years. That sounds like a long time, but in the life of a star, it's a blink. During that time, the sun is unstable. It pulses. It throws off huge clouds of gas. It flickers, and deep inside, the core is still collapsing. And then it happens. The helium flash. When the core reaches a critical density and temperature, about 100 million degrees, something finally ignites. Helium starts to fuse. But it doesn't start slowly, it starts with a bang, a runaway reaction. The entire core ignites in a matter of seconds. The energy release is immense. For a brief moment, the sun's core generates as much power as an entire galaxy. But here's the weird part. You wouldn't see it from the outside. The flash happens deep inside, and the outer layers absorb most of the energy. The star temporarily dims. Then it readjusts. After the helium flash, the sun enters a new phase. It's called the horizontal branch. The core is now burning helium into carbon and oxygen. The star shrinks a bit, becomes more stable, but not for long. Because helium ash, carbon and oxygen, is also inert. It piles up in the core, just like the hydrogen ash did. And once again, the core runs out of fuel. This is the asymptotic giant branch. The star expands again. It becomes a second red giant. This time it's even larger and more unstable. The shell burning of helium and hydrogen creates a complex, layered structure. The star pulses. It throws off massive amounts of material. The outer layers are ejected in huge, slow-moving winds, and this is where the beauty begins. Over the course of a few 100,000 years, the Sun sheds its entire outer envelope. All that gas, all that plasma, all the material that once made up the star's outer layers drifts away into space. It forms a glowing cloud around the dying core. That's what we call a planetary nebula. It's a misnomer. It has nothing to do with planets, but it's one of the most stunning sights in the universe. A shell of ionized gas, lit up by the intense ultraviolet radiation from the exposed core. It glows in reds, blues, greens. It's a final, beautiful gasp. And at the centre of that nebula is what's left. The core, a white dwarf. The Sun's white dwarf is a strange object. It's about the size of Earth. That's it. A sphere roughly 12,000 kilometres across. But it contains about half the mass of the original Sun. Think about that. You take a star that was 1.4 million kilometres across, compress it down to a ball the size of our planet, and you get something so dense that a teaspoon of its material would weigh about 5 tons. It's made of carbon and oxygen, essentially a giant diamond, slowly cooling in the dark. The white dwarf has no fusion, no source of energy. It's just hot, extremely hot. About 100,000 degrees at the surface. It glows white hot from residual heat. But over time it cools, it fades. It takes trillions of years, not billions, trillions, for a white dwarf to cool down enough to stop glowing. And when it finally does, when it reaches the ambient temperature of the universe, it becomes a black dwarf. A black dwarf is the ultimate end state, a cold, dark, Earth-sized lump of crystallized carbon. Invisible. Dead. The universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs are still glowing faintly. But if you wait long enough, if you wait a few quadrillion years, the Sun's white dwarf will join that club. So what's left? The solar system is empty. The inner planets are gone. The gas giants are still out there, drifting on their expanded orbits. But they're cold and dark without the Sun's warmth. Their atmospheres freeze. Their storms die. They become dead worlds orbiting a dead star. And the white dwarf just sits there, silent, cold, slowly fading. But here's the thing. The planetary nebula doesn't last forever. After a few tens of thousands of years, the gas dissipates into interstellar space. The beautiful, glowing cloud fades away, and all that's left is the white dwarf and the dead planets orbiting it. The entire solar system becomes a ghost system. A faint dim memory of what once was. No life. No light. No warmth. Just the quiet hum of a cold star, drifting through the galaxy for the rest of time. And that's the baseline. That's the certain end. The one that will happen if nothing else interferes. No wandering stars, no rogue black holes, no alien civilizations. Just the slow, predictable death of a stable, middle-aged star. But here's the part that gets me. That white dwarf will keep orbiting the center of the Milky Way. The galaxy will keep turning. Stars will be born and die. Andromeda will collide with us. Eventually, the universe itself will grow old and cold, but the Sun's white dwarf will still be there long after the last stars have burned out. It will be one of the last objects in the universe to decay through a process called proton decay, if that even happens. So when we talk about the end of the solar system, we're not just talking about the death of a star. We're talking about the death of everything we know. And it's not a surprise. It's not a random accident. It's written into the physics of the star itself. It's an inevitability. A slow, beautiful, heartbreaking inevitability. But before you get too sad, remember, we still have about 1 billion years before the oceans boil. That's 1 billion years of life, of growth, of change. 1 billion years to figure out how to leave, or how to fight, or how to accept it. And that's a story for another time. Right now, we're here. The sun is shining. The earth is spinning. And we're just passengers on a rock watching the clock. But what do we actually have? Not the earth, not the sun, but us, humanity. We live in a narrow window of cosmic time. a brief moment when the universe is warm enough for liquid water and cool enough for complex chemistry. We are not at the beginning of the universe, and we are nowhere near its end. We exist during the stelliferous era, the time when stars are alive and burning. It's the only era we know, and it will eventually end. The sun's death marks the end of our era for our solar system, but the universe as a whole will continue for trillions upon trillions of years, long after the last star has winked out. The timeline is staggering when you put it in perspective. The universe is about 13.8 billion years old. The sun will last another 5 billion years before it begins its transformation into a red giant. That means the entire lifetime of the sun, from birth to white dwarf, is about 10 billion years. The universe is already halfway through that lifespan for stars like our sun. But compared to the timescales that follow, the stelliferous era is just a blink. The degenerate era will follow, when white dwarfs, neutron stars, and black holes dominate the cosmos. That era will last for an incomprehensible 10 to the 37th million years. After that comes the black hole era, and finally the dark era, when even black holes have evaporated and the universe is nothing but a cold, thin soup of particles and radiation, forever drifting apart. But we are talking about the sun, and the sun is our anchor. It is the only star we will ever touch, the only star that has ever mattered to life on Earth, and when it dies, it will not do so quietly. It will rage. It will expand. It will consume. It will throw off its outer layers in a final spectacular display of beauty and violence. And then it will become a cold, dark cinder. There is a certain irony in all of this. The sun is the source of all energy for life on Earth. Every calorie you have ever eaten, every drop of rain that fell, every breath of wind that blew, all of it traces back to the sun. The sun made the oxygen in the air. The sun made the fuel that powers our civilization. The sun is the reason we exist at all, and yet the sun will also be the reason we cease to exist. It gives, and it takes away. That is the nature of stars. There is also a deep historical context to our understanding of stellar evolution. For most of human history, we did not know that stars changed at all. The ancient Greeks believed the heavens were perfect and unchanging. The stars were fixed points of light, eternal and immutable. It wasn't until the early 20th century that astronomers like Arthur Eddington and Subrahmanyan Chandrasekhar began to understand the physics of stellar interiors. They realized that stars are not static objects. They are dynamic, evolving, and ultimately mortal. The realization that our own sun will one day die was a profound shift in human consciousness. It forced us to confront the fact that our solar system is not permanent. Our planet is not permanent. Our species is not permanent. Everything we have ever known is temporary, suspended in a fragile balance of gravity and fusion. This knowledge has shaped philosophy and art in ways we are still processing. When you look at a painting of a sunset, you are looking at a moment of beauty that will one day be the last sunset. When you read a poem about the stars, you are reading about lights that will one day be extinguished. The awareness of cosmic mortality is a uniquely human burden. We are the only species on Earth that knows the sun will die. We are the only species that can look at a star and calculate its future. We are the only species that can grieve for a world that does not yet exist, a world that will be consumed by fire eons from now. But there is also something beautiful in this knowledge. The fact that the sun will die means that every moment of sunlight is precious. Every day that the sun rises is a gift, a temporary reprieve from the inevitable. The heat on your skin, the light in your eyes, the warmth that makes life possible. It is all borrowed time, and that makes it sacred. If humanity survives long enough, we will have to leave. We will have to abandon Earth long before the sun becomes a red giant. The first billion years will see the oceans begin to boil. The atmosphere will thicken with water vapor, trapping more heat, creating a runaway greenhouse effect. The land will scorch, the last plants will wither, the last animals will perish. The Earth will become a barren, hellish world, more hostile than Venus. We will have to leave, if we can. If we cannot, we will die here, along with every other living thing. The exodus from Earth will be the greatest undertaking in human history. We will have to spread out among the stars, carrying our culture, our art, our memories, and our genes to distant worlds. We will have to build habitats around other stars, or on worlds that orbit dead stars themselves. We will have to become a true interstellar species. And even then, we will be running from the eventual death of the sun. But the sun's death is not the death of the universe. There are other stars. There will always be other places to go, as long as there are stars in the sky. But what happens when those stars also die? The universe will eventually become a cold, dark place. The last stars will burn out in about 100 trillion years. After that, there will be no more light from fusion, only the faint glow of white dwarfs and the dim radiation from black holes. And eventually, even those will fade. The universe will become a place of eternal darkness, eternal cold, and eternal silence. And yet, there is a possibility, a hope. It is possible that intelligent life, if it survives long enough, could create its own stars. We could harness energy on unimaginable scales. We could build Dyson spheres around dying stars to capture their last light. We could even engineer new stars, igniting fusion in hydrogen clouds to create new sources of energy. We could delay the heat death of the universe, at least locally, but we cannot stop it forever. Thermodynamics is a harsh mistress, and entropy always wins. In the end, the sun's death is just one death among countless. It is the death of our world, but not the death of all worlds. It is the end of our story, but not the end of all stories. The universe will go on without us. Stars will be born and die in other galaxies, on other planets, in other systems, and never know that we existed. Our fossil record, our artifacts, our radio signals, our debris, all of it will be erased by time and distance. Nothing we build will last forever. Nothing we write will survive the sun's expansion. Every monument, every book, every photograph, every memory, all of it will be vaporized or scattered into the void. But does that make it meaningless? No, because meaning is not found in permanence. Meaning is found in the moment. The fact that the sun will die does not make life less precious. It makes life more precious. Every second you are alive, you are part of a rare and fleeting phenomenon. A conscious mind in a universe that is mostly empty and unconscious. You are the universe waking up, looking at itself, and understanding its own beauty. The sun will die. The earth will be consumed. Humanity will either transcend or perish. But right now, in this brief flash of time, we get to exist. We get to ask questions. We get to wonder about the future. We get to look up at the stars and know that they too will one day fade. And that knowledge, that awareness, is itself a kind of immortality. Because as long as we remember, as long as we think, as long as we care, the universe is not just a cold mechanical machine. It is a home. It is a story, and we are the ones telling it. So let us tell this story well. Let us not waste the time we have. Let us explore, create, love, and learn. Let us leave behind something worthy of the brief burning light we have been given. And when the sun finally expands, when it swallows the inner planets and turns the sky red, let us hope that our descendants, wherever they are, look back at this ancient dying star and remember. Remember that it was once the heart of a world full of life. Remember that it was once our sun, and then they will turn away. They will look to the next star, the next home, the next chapter in the long unfolding story of life in the universe. Because that is what we do. We survive, we adapt, we move forward. Even when the sun dies, the light does not go out. It just moves somewhere else. And that is the most beautiful thing of all. But what if the end doesn't come from within? What if it comes from something passing through our cosmic backyard? Something we can't stop, can't predict with any real certainty, and can barely even see coming until it's already here. I'm talking about stellar close encounters. This is a relatively new understanding in astronomy, a sobering realization that our sun isn't some stationary king sitting motionless on a throne. No, it's moving. It's travelling through the Milky Way at about 500,000 miles per hour, dragging its entire family of planets, moons and comets along for the ride, and in that journey it occasionally runs into other stars. Think about that for a second. The sun is a wanderer, just like everything else. We think of the solar system as stable, fixed, and permanent. But in reality, it's a fragile little bubble hurtling through a crowded galactic neighborhood, and sometimes that bubble gets popped. The galaxy is full of stars, hundreds of billions of them, all moving in their own orbits around the supermassive black hole at the center. Most of the time, those orbits keep them far apart. Space is mostly empty after all. But every now and then, gravity plays a cruel trick. A star wanders a little too close to another star, and everything changes. When we talk about stellar flyby, we're not talking about a star crashing into the sun. That's almost impossible. The distances involved are still enormous. But you don't need a direct hit to cause chaos. You just need a star to get close enough to pull on things. And by close, I mean within a few light years. That might sound impossibly far, but on a galactic scale, it's a hair's breadth. The frequency of these events is something we've only recently begun to understand. Thanks to precise measurements from space telescopes like Gaia, we now know that a star passes within 1 light year of the Sun roughly once every 500 million years. That's not a lot by human standards, but on geological and evolutionary timescales, it's practically a guarantee. You don't need to be a mathematician to see that the odds are not in our long-term favour. The first thing that happens when a star wanders into the outer reaches of the solar system is that it pokes the Oort cloud. Now, the Oort cloud is that vast spherical shell of icy debris that surrounds the solar system, stretching out nearly a light year from the Sun. It's where long-period comets come from, and normally it's a peaceful, frozen reservoir just sitting there in the dark. But a passing star acts like a gravitational bulldozer. It tugs on those icy bodies, sends them tumbling out of their stable orbits, and initiates what we call a comet shower. Suddenly, instead of a trickle of comets heading toward the inner solar system, you get a flood. Hundreds, thousands, maybe even millions of comets get redirected toward the Sun, and some of those comets are going to hit Earth. Now, we've seen what happens when just one big rock hits us. A comet shower lasting tens of thousands of years, with impacts happening every few decades, would be a catastrophe beyond anything we've ever experienced. Some scientists have linked these periodic comet showers to mass extinction events in Earth's past. There's a controversial theory that the extinction of the dinosaurs might have been influenced by a passing star jostling the Oort cloud. It's not proven, but the timing fits oddly well with some known stellar flybys. So you have to wonder, how many times has life on Earth been interrupted by a random passerby in the night? The most famous example of a future close encounter is Gliese 710. You've probably heard the name. It's a small, dim star, an orange dwarf about 60% the mass of the Sun. And right now it's heading toward us at a leisurely pace of about 31,000 miles per hour. But here's the thing. Gliese 710 is going to pass right through the Oort cloud in about 1.3 million years. That's not a long time, cosmically speaking. It's practically tomorrow. And when it does, it will get closer than any other star has in the last few million years. Current calculations suggest it will come within about 10 to 12,000 astronomical units of the Sun. That's deep inside the Oort cloud. It will be bright enough to be visible to the naked eye from Earth, a brilliant new star in the sky. But don't let the beauty fool you. Its gravitational wake will send a swarm of comets hurtling into the inner solar system. And again, it's not going to hit us, but the secondary effects, the impacts, the dust, the potential climate shifts, they could be catastrophic. But that's just the beginning. What happens when a star gets even closer? Because Gliese 710 is just the best studied example, but it's far from the worst case scenario. Let's escalate the situation. Imagine a star passing at 1,000 astronomical units from the Sun. At that distance, the Oort cloud doesn't just get perturbed, it gets stripped. The entire outer shell of icy debris gets torn away and dragged off into interstellar space, leaving our solar system as a much smaller, emptier place. We lose our cometary reservoir. That changes the long-term dynamics of the entire system. The cosmic environment we take for granted is gone. Now, imagine a star passing at 100 astronomical units. That's about 2.5 times the distance from the Sun to Pluto. At that range, the gravitational influence isn't just felt by comets, it hits the planets. Neptune's orbit, which is already a delicate balance, becomes deeply unstable. The outer planets start to wobble. Their orbits get stretched and tilted. This is where things get really messy, because the solar system isn't built like a clockwork machine. It's more like a bunch of marbles balanced on a spinning plate. And when you jiggle the plate, the marbles start to fall. Neptune gets kicked out of its orbit, then it interacts with Uranus, which then messes with Saturn, and before you know it, you have a chain reaction that can eject planets entirely from the system or send them crashing into each other. And then we get to the really terrifying scenario. A star passing at just 10 astronomical units from the Sun. That's closer than Saturn. At that distance, the intruder is right in our neighbourhood. The gravitational forces are enormous. Jupiter and Saturn, the gas giants, are severely disrupted. Their massive gravitational fields, which normally act as a protective shield, become a weapon. Jupiter is often called the solar system's vacuum cleaner because it sucks up so many dangerous comets and asteroids. But when its orbit is thoroughly scrambled, it becomes an engine of destruction. It can slingshot entire planets out of the solar system like a cosmic billiard ball. The complex dance of orbital resonances that has kept things stable for billions of years collapses into chaos. Mercury could be flung into the Sun, Mars could be ejected, Earth could be pulled into an orbit that freezes it or fries it. The inner solar system becomes a shooting gallery, and these aren't just hypothetical fantasies. We've seen the evidence. Astronomers have observed other star systems that have clearly been visited by passing stars. You can see the scars in the debris disks around other suns, the warped orbits, the missing planets, the clouds of dust that speak of recent collisions. It's not a matter of if it will happen to our system. It's a matter of when. Now, let's talk about rogue planets, because a close stellar encounter doesn't always just bring a star. Sometimes the star brings friends. It's estimated that there are billions of rogue planets wandering through the Milky Way, planets that were ejected from their own star systems by gravitational interactions. They drift alone in the darkness, cold and invisible. And if a star passes close to our Sun, it might be dragging a few of these rogues along with it. A rogue planet entering the solar system would be a planetary collision waiting to happen. Even a small rogue, say the size of Mars, could completely destabilize Earth's orbit if it passed close enough. And we wouldn't see it coming until it was almost too late, because rogue planets don't emit light. They're dark, ghostly wanderers. We'd only spot them when they started reflecting sunlight, and by that point they'd be moving at tens of thousands of miles per hour. There's also the collapse of Jupiter's protective shield. I mentioned it earlier, but it deserves more attention. Jupiter is a cosmic bodyguard. Its enormous gravity deflects a huge number of comets and asteroids that would otherwise regularly slam into Earth. But if a passing star perturbs Jupiter's orbit even slightly, that protection goes away. Suddenly, Earth becomes a target for everything that was previously blocked. The impact rate might increase 100-fold. Instead of a major extinction event every 100 million years, you could see one every million years. And that's not survivable for complex life. We'd be bombarded back to the Stone Age, or worse, back to the age of single-celled organisms. And then there's the galactic carousel theory. This is a more controversial idea, but it's gaining traction. It suggests that the Sun's orbit around the centre of the Milky Way is not smooth. It bobs up and down through the galactic disk, and every time it crosses the densest part of the disk, it experiences more gravitational interactions. These crossings, which happen roughly every 30 to 40 million years, might correlate with the major extinction events on Earth. The timing is suspicious. There's a pattern in the fossil record that seems to match that rhythm. It's not proof, but it's a hell of a coincidence. It means that the entire galaxy is alive with motion, and our little solar system is just a piece of flotsam being tossed around by currents. So what are the actual odds? Statistically speaking, the probability of a civilization-ending stellar encounter within the next billion years is around 1%. That doesn't sound like much, does it? But let's put that into perspective. 1% over a billion years is a lot more than 0%. It's practically a certainty if you extend the timeline far enough. And remember, civilization has only existed for a few thousand years. We've been lucky. We've lived through a quiet period in the galaxy's history. But the clock is ticking, and the odds don't get better with time. Think about Gliese 710 again. It's coming. There's no doubt about that. And while it probably won't end the world, it will definitely change it. The comet shower it triggers could be severe enough to cause mass extinctions. And that's just the one we know about. There could be other stars out there, dim red dwarfs or brown dwarfs that we haven't detected yet, that are already on a collision course with our Oort cloud. We might not see them until they're already doing their damage. And here's the really humbling part. We can't stop it. We have no technology, no plan, no way to push a star away. If a rogue star enters the solar system, we just have to ride it out. And if it gets too close, we don't ride it out at all. We get crushed, ejected, or fried. That's the reality. The universe is not a safe place. It's a dynamic, violent, and indifferent arena. So why am I telling you all this? Because these are not just science fiction scenarios. They are real. They have happened to other stars, and they will happen to ours. The only question is when, and how bad it will be. We live on a tiny rock orbiting an average star in an average galaxy, and we are completely at the mercy of the cosmic neighbourhood. And that neighbourhood is not empty. It's full of motion, full of potential danger, and full of passing strangers who might not be friendly. The sun is a traveller, and so are we. And every now and then, in the dark vastness of space, two travellers cross paths. When they do, nothing is ever the same. So next time you look up at the night sky, remember that the stars are not just distant lights. They are moving, they are coming and going. And one day, one of them will come a little too close. And that, my friends, is a discovery we are still trying to fully understand. It's a humbling reminder that we are not in control. We never were. We are just passengers on a ship sailing through treacherous waters, hoping the next storm won't sink us. But that's okay, because knowing the danger is the first step to surviving it. And if we ever want to outlast the sun itself, we need to understand every way the solar system can end. Even the ones that come from outside. Even the ones that arrive without warning. Because the universe doesn't care about our plans. It just keeps moving, and we have to move with it. Let's go deeper into that dark place, the space between the stars where these wanderers hide. Because the most terrifying aspect of stellar close encounters is not the star itself, but what it might be carrying. We touched on rogue planets, but let's linger on that horror. A rogue planet is a world without a sun. It has been ejected from its original system, often through violent gravitational interactions with larger planets or passing stars. It drifts through the cold void, its surface frozen to near absolute zero, its atmosphere, if it ever had one, frozen solid and collapsed onto the ground. These objects are utterly invisible to our current survey telescopes. They emit no light. They reflect almost none. They are the perfect predators. Now imagine a stellar flyby, say a red dwarf passing within a few hundred astronomical units. It is not just the star that enters our system. It is likely accompanied by a swarm of its own planets, captured objects, and possibly rogue worlds it's picked up along its journey through the galaxy. This stellar intruder is a nomadic hunter, dragging its family of orphans through the darkness. And some of those orphans, those rogue planets, could be massive. Think of a gas giant the size of Jupiter, cold and dead, but with a gravitational pull just as strong. If such an object enters the solar system, it doesn't need to hit us. It just needs to pass close enough to pull Earth out of its habitable zone. The math is brutal. A rogue planet with the mass of Saturn passing within the orbit of Mars would tug on Earth's orbit with enough force to lengthen our year, tilt our axis, or send us spiralling inward toward the Sun, or outward toward the frozen abyss. We wouldn't feel the change immediately. It would take decades or centuries. The orbit would slowly elongate, seasons would become more extreme, and then the climate would collapse. Ice would creep from the poles. The oceans would boil or freeze, and all the while that dark wanderer would slip away into the night, unseen, unaccounted for, leaving a dead world in its wake. This is not idle speculation. We have found direct evidence of these gravitational kidnappings in other star systems. The star HD 106906 has a planet that orbits at a staggering distance of over 700 astronomical units from its parent star, a clear sign that it was flung out there by a passing star or a massive planetary instability. And if that can happen there, it can happen here. In fact, some astronomers believe that our own solar system might have already experienced a similar event in its youth. There is a theory, controversial but compelling, that the hypothesized Planet 9, a massive world thought to be lurking in the outer darkness of our solar system, might actually be a captured rogue planet. We haven't found it yet. It remains a ghost. But if it is out there, its presence proves that the solar system has been visited before, and that it can happen again. Let's now turn to the historical record, written not in books, but in the crust of the Earth and the ice of its poles. Geology and paleontology give us a chilling timeline. The fossil record shows at least 5 major mass extinction events and countless smaller ones. We have long attributed these to volcanic eruptions, asteroid impacts, and climate shifts. But there is a growing body of evidence that suggests some of these catastrophes might be linked to close stellar encounters. The timing is suspicious. The extinction of the dinosaurs 66 million years ago is famously tied to a single asteroid impact. But what if that impact was not a random event? What if it was part of a comet shower triggered by a passing star? We know that a star called Schultz's star, a dim red dwarf, passed within a light year of the Sun about 70,000 years ago. That is practically yesterday in cosmic terms. It passed right through the Oort cloud, and while it did not cause a noticeable extinction on Earth at that time, the timeline is still within the range of geological uncertainty. What if a similar encounter, much closer, happened 67 million years ago? The physics supports it. The evidence is circumstantial, but it is there. We have found layers of iridium, an element rare on Earth but common in comets, spread across the globe, and we have found that the frequency of comet impacts on Earth seems to follow a rough cycle of about 26 to 30 million years. That cycle matches the timing of our Sun's oscillation through the galactic plane. It is called the Shiva hypothesis, named after the Hindu god of destruction. The idea is that as the Sun bobs up and down through the crowded disk of the galaxy, it encounters denser regions of stars and gas clouds, which perturb the Oort cloud and send comets hurtling inward. The last major peak of that cycle, geologically speaking, is about 10 million years from now. We are in a relatively quiet period, but the clock is ticking, and let us not forget the historical perspective from human civilization itself. For most of history, humans looked at the stars and saw fixed, eternal lights. The idea that the stars moved, that they could come close enough to harm us, was unthinkable. The earliest astronomers, the Babylonians, the Greeks, the Chinese, they tracked the wandering planets, the wanderers, but they considered the fixed stars to be an unchanging backdrop. It was not until the 18th century that astronomers began to suspect the truth. Edmund Halley first noticed that some stars had moved slightly from their positions recorded by the ancient Greeks. He discovered proper motion, the slow drift of stars across the sky. That was the first crack in the illusion. Then in the 20th century we began to measure radial velocity, the speed at which stars move toward or away from us, and we started cataloguing their trajectories. We built massive databases, and what we found was a universe in motion, a swirling, chaotic dance. The discovery of Gliese 710's trajectory was a wake-up call. Suddenly the threat was not just asteroids or supernovae. It was something more fundamental. It was the instability of our position in the galaxy. Think about the implications for the future of humanity. If we survive the next millennium, if we become a spacefaring civilization, this knowledge becomes a curse. We will be able to predict these encounters with increasing accuracy. We will know exactly when the next star is coming, exactly how close it will get, and exactly how much damage it will do. But knowing does not mean we can stop it. Imagine the scenario. In 1 million years, our descendants, if they exist, will watch the bright point of Gliese 710 grow brighter in the sky. They will track its approach. They will run simulations. They will see the Oort cloud begin to tremble. They will see the orbits of the outermost planets start to waver. And they will know that within a few thousand years, the heavens will rain fire. What do you do with that knowledge? Do you build shelters? Do you try to deflect the comets? Do you abandon Earth entirely and flee to distant star systems? Those are the terrible choices that a stellar encounter forces upon a civilization. We are not there yet. We are still infants, barely able to detect these threats, let alone respond to them. But the time will come when our descendants will have to face the music. There is also a deeper, more philosophical terror here. The Milky Way is a city of 100 billion stars, each one moving on its own path. Collisions are rare, but interactions are common. Every star in the disk of the galaxy will have hundreds of close encounters over the lifetime of the universe. That means that the solar system, as we know it, is a temporary configuration. It is not a permanent arrangement. It is a fleeting moment of stability in a sea of chaos. In 5 billion years, the Sun will swell into a red giant and consume the inner planets. But that is a gentle end compared to what could happen much sooner. A passing star could tear the solar system apart long before the Sun dies. Earth could be ejected into interstellar space, a frozen rogue world carrying the last remnants of life into the darkness. Or it could be thrown into the Sun, a final fiery cremation. Or it could be captured by the passing star, becoming a hostage in a new alien system. Those are not just possibilities. They are inevitabilities over the vast, deep time of the universe. The only reason we are safe right now is that the timescales are long. But long does not mean never. Consider the chaotic orbits of the inner planets. Mercury is particularly susceptible. Its orbit is already unstable over billions of years. There is a small but real chance that Mercury could be thrown into the Sun or into Venus within the next few billion years, even without any external perturbation. Now add a passing star to that equation. You don't need a direct hit, you just need a nudge. A star passing at a few hundred astronomical units could provide that nudge. Suddenly, Mercury's instability becomes a certainty, and when Mercury goes, it doesn't just disappear. It sends a shock wave through the inner system. The gravitational dominoes fall, Mars gets perturbed, the asteroid belt gets stirred up, and Earth, sitting right in the middle, gets caught in the crossfire. This is the butterfly effect on a cosmic scale. A star half a light year away could, through a chain of gravitational interactions, trigger an apocalypse on Earth millions of years later. And let us talk about the long-term stability of our planetary system as a whole. Computer simulations have shown that the solar system is not stable. It is technically chaotic. The orbits of the outer planets, especially Jupiter and Saturn, have subtle resonances that can amplify over tens of millions of years. Without any outside influence, the solar system will eventually rearrange itself. There is a small but non-zero chance that Mars will be ejected, that Mercury will collide with Venus, that Earth will be dragged into a new, deadly orbit. That is the baseline chaos. Now add a passing star. The star acts as a perturbation that amplifies that chaos. It pushes the system over the edge. It accelerates the inevitable. The solar system is a clock that is slowly winding down, and a close stellar encounter is a hammer that shatters the clock completely. We must also consider the galactic environment. The Sun is currently in a relatively quiet and sparse region of the galaxy called the local bubble. But it was not always there, and it will not stay there. The Sun's orbit around the galaxy is not a perfect circle. It is an epicyclic motion, a wobbly path that carries it through denser and thinner regions. When the Sun passes through a giant molecular cloud, a stellar nursery filled with dense gas and dust, the gravitational effects on the Oort cloud are enormous. Not only does the gas and dust exert a drag force, but the stars embedded in that cloud can also have close encounters. We have found evidence that the Sun may have passed through such a cloud a few million years ago, leaving a trail of dust in the solar system. It is entirely possible that these passages have shaped the evolution of life on Earth in ways we do not fully understand. Perhaps the ice ages, the mass extinctions, the very rhythm of evolution are all tied to the sun's journey through the galaxy. We are not just passengers on a ship. We are plankton drifting in a cosmic ocean, and the currents of that ocean are determined by the motions of a billion stars. And so we return to the fundamental truth. The solar system will end. It will not end because the sun explodes. It will not end because we destroy ourselves. It will end because the universe is restless. It will end because a visitor, an unknown and unknowable stranger from the deep, will come calling. And when that day comes, all our history, all our art, all our science, all our love and hate and hope and fear will be nothing more than a fleeting memory in the cold, empty space between the stars. The only question is whether we, or our descendants, will see it coming, and whether they will have the strength, the wisdom, and the will to face it. Because that is the final lesson. We are not masters of our destiny. We are guests in a dangerous house, and the landlord is coming to collect. Let us hope we are ready. But if the history of life on Earth teaches us anything, it is that we are never ready. We just survive. Or we don't, and the galaxy moves on, indifferent and eternal. From this cosmic inheritance of rogue planets and dying stars, we now turn to a threat far more absolute, far more terrifying in its silent, invisible approach. The black hole. Think about that number for a moment. The Milky Way galaxy, our home, is estimated to contain somewhere between 10 million and 1 billion stellar mass black holes. That is not a typo, a billion. These are the collapse cores of dead massive stars, remnants of supernovae that have long since faded from view. They are everywhere, drifting through the interstellar void like submerged icebergs in a dark ocean. And they are, for all practical purposes, invisible. We tend to imagine black holes as cosmic vacuum cleaners, sweeping up everything in their path with some kind of hungry intent. This is a misconception, and it is a dangerous one. A black hole does not suck. It does not reach out with grasping tendrils. It simply sits there, possessing an immense concentration of mass, and it warps the fabric of space-time around it. If you replaced our Sun with a black hole of the exact same mass, the Earth would continue to orbit it perfectly, year after year, growing colder and darker, but never being pulled in. The gravity at this distance would be identical. The misconception of the cosmic vacuum cleaner comes from movies and sensationalist headlines. What a black hole does is create a gravitational well so deep that once something crosses a certain boundary, the event horizon, there is no escape. But outside of that boundary, it behaves like any other massive object. It just happens to be a lot smaller and a lot denser. So when we talk about a black hole wandering through the solar system, we are not talking about it swallowing everything up from light years away. We are talking about a close encounter, and the effects of that encounter depend entirely on how close it gets. Let's imagine a worst-case scenario. A black hole, perhaps 20 times the mass of our Sun, is drifting through the galaxy at a modest speed relative to our solar system, say 50 kilometers per second. We do not see it approaching. It is not accreting gas, so there is no X-ray glow, no radio emission. It is just a patch of perfect, absolute darkness moving against the background stars. If you were looking in its direction, you would see nothing. The stars behind it would simply appear to shift and distort as if you were looking through a warped lens. And then, one day, it is here. At a distance of 100 astronomical units, roughly the outer edge of the scattered disk of comets and icy bodies beyond Neptune, the black hole's gravity would begin to have a noticeable effect. 100 ATU is far, far away from us. But the black hole is so massive that its gravitational influence would start to pull and tug on the outer planets. Neptune and Uranus would begin to wobble in their orbits, their paths slowly becoming elliptical, chaotic. This would trigger a cascade of perturbations. The Kuiper belt, that vast ring of icy debris beyond Neptune, would be violently stirred. Objects that have circled the Sun in quiet isolation for 4.5 billion years would suddenly be flung inward toward the inner solar system. For the next few thousand years, Earth would experience a barrage of cometary impacts, unlike anything since the late heavy bombardment. Entire oceans could be vaporized. The atmosphere could be stripped. But this is just the beginning. If the black hole gets closer, if it passes within 1 astronomical unit, the distance from the Earth to the Sun, then we are in truly catastrophic territory. At 1 AU, the black hole would be not far from Earth itself. Its gravity would tear the planets from their orbits. Earth, at this distance, would experience what planetary scientists call tidal disruption. The gravity from the black hole would pull harder on the side of Earth facing it than on the far side. This differential, the tidal force, would literally stretch our planet. The crust would crack, the mantle would be pulled apart, the core would be exposed, and within a matter of minutes, the Earth would be torn into a stream of debris, a long, thin ribbon of molten rock and vaporized iron spiraling down toward the event horizon. No warning, no escape. Just a final catastrophic pulse of energy as the last of our world crosses the point of no return. But there is an even closer, even more horrific scenario. Imagine the black hole passing not at 1 AU, but at a distance of just 10 solar radii from the Sun itself. That is about 4.5 million miles. At this range, the black hole would begin to strip material from the Sun. A stream of superheated plasma would arc across space, feeding the black hole's accretion disk. And the Earth? The Earth would be subjected to what is called spaghettification. This is not a technical term used to be dramatic. It is the literal name. The tidal forces would be so extreme that the planet would be stretched into a long, thin strand of matter, like spaghetti. You would not feel it because you would be dead long before the planet reached that state. But in a purely physical sense, our entire world would be deformed into a glowing, elongated ribbon of debris, wrapping around the black hole like a cosmic thread. The Moon, the other planets, everything in the inner system, would meet a similar fate. The solar system would not end in a bang. It would end in a quiet, gravitational unravelling, a slow dissolution of order into chaos. Now, let us talk about the elephant in the room. Sagittarius A star, the supermassive black hole at the centre of our galaxy. It is 4 million times the mass of our Sun. It sits 26,000 light-years away. Right now, it is quiet. It is not actively feeding, but supermassive black holes are known to have active phases. They go through periods of intense accretion, emitting jets of radiation that can sterilize entire galaxies. If Sagittarius A star were to suddenly flare up, if it were to consume a large cloud of gas or a star in its vicinity, the resulting radiation could be lethal across vast distances. But here is the thing. We are 26,000 light-years away. The radiation would travel at the speed of light. We would not see it coming. One moment the night sky is normal. The next, a flare of gamma rays and X-rays sweeps over the solar system, stripping away our ozone layer, irradiating the surface, and ending all complex life within a matter of seconds. It is a low probability event, but it is not zero. There is another, more insidious possibility. Intermediate mass black holes. These are the missing link. Objects between 100 and 100,000 solar masses. We know they exist, but we do not know how many there are or where they hide. They could be lurking in the dense star clusters surrounding the galactic center. They could be wandering through the galactic disk, and if one of them passed through the outer reaches of the solar system, its gravity would be enough to destabilize the entire Oort cloud, sending a wave of comets inward for millions of years. It would not be a sudden apocalypse, it would be a slow, grinding extinction, a rain of fire that could last longer than the entire history of the human race. And then there are the hypervelocity black holes. When two black holes merge, the resulting collision can kick the newly formed object to incredible speeds, thousands of kilometers per second. These are the cosmic cannonballs. A hypervelocity black hole could cross the entire galaxy in a few million years. It could come from any direction at any time. We would never see it until it was too late. In fact, there is a theory that a population of these rogue black holes exists, moving so fast that they are essentially invisible to our current surveys. They are the ultimate stealth threat. But let us be realistic. The probability of any of these scenarios happening in the next million years is incredibly low. The solar system has been stable for over 4 billion years. The chances of a random black hole wandering through our neighbourhood are minuscule, but here is the uncomfortable truth that astronomers have to live with. Low probability is not zero probability, and in a universe governed by time scales of billions of years, low probability events become near certainties. If you wait long enough, everything that can happen will happen. The solar system will not last forever. It will be destroyed either by the sun, by a rogue star, by a supernova, or by a black hole. The only question is which one gets us first. If a black hole encounter were to happen, it would be without warning. There would be no countdown, no dramatic build-up, no chance to say goodbye. One day the sky is normal. The next day the planets begin to wobble. A week later the Earth is torn apart. Or perhaps the X-ray flash comes first, and we never even see the black hole. We simply cease to exist, our planet sterilized in an instant by a burst of radiation that travelled across the galaxy for 20,000 years, arriving at exactly the wrong moment. This is the nature of black holes. They are not evil. They are not malevolent. They are simply the most extreme consequence of gravity in the universe. And they are out there, billions of them. Drifting through the darkness, waiting for nothing, but capable of ending everything. So when we talk about the end of the solar system, we must include black holes. Not because they are likely, but because they represent the ultimate unknown. They are the cosmic wildcard. A rogue planet is slow, a supernova is predictable, but a black hole can come from anywhere, at any time, and there is absolutely nothing we could do to stop it. Not with our current technology, not with any technology we can imagine. If a black hole enters the solar system, we are not surviving it. We are not evacuating. We are not building bunkers. We are becoming part of its accretion disk, a brief flash of heat as our atoms spiral into oblivion. And that is the final, sobering truth. The universe is vast, it is ancient, and it is full of dangers we can barely comprehend. We have been lucky so far, 4 billion years of relative stability, but luck runs out. It always does. The question is not if the solar system will end. The question is how, and when. The black hole option is the most terrifying because it is the most absolute. There is no aftermath, no slow decline, no gradual cooling. There is just a moment of chaos and then nothing. The Earth, the Sun, the planets, all of it, gone. Replaced by a faint ring of glowing debris orbiting an invisible point in space. And the galaxy continues on, indifferent as ever. The black hole moves on, its trajectory barely altered by the tiny morsel it consumed. It continues its silent journey through the void, unseen, unknown, until it meets another star, another planet, another world that is simply in the wrong place at the wrong time. And somewhere out there, maybe, another civilization is having the same thought. Or maybe not. Maybe they already met their black hole, and we just have not found their remains yet. So we return to the central theme of this entire narrative. We are not masters of our destiny. We are guests in a dangerous house, and the landlord is coming to collect. Let us hope we are ready. But if the history of life on Earth teaches us anything, it is that we are never ready. We just survive, or we don't, and the galaxy moves on, indifferent and eternal. The indifference of the galaxy is perhaps the most difficult concept to truly internalize. We project our own values, our own fears, our own sense of importance onto the cosmos. We imagine that the universe must care about us, that there must be some cosmic justice, some grand narrative. But a black hole does not care. It does not know that it has destroyed a civilization. It does not register the passing of 1 billion years or 1 billion souls. It is a pure mathematical object, a solution to Einstein's field equations, a region of space-time where gravity has won its final, absolute victory over all other forces. And in that victory, it has erased everything that once was. Consider the historical context of our understanding. When Jean Michel first proposed the idea of dark stars in 1783, he was a clergyman and a geologist working within the framework of Newtonian gravity. He calculated that if a star were sufficiently massive and compact, its escape velocity would exceed the speed of light. Light itself would be trapped, the star would be invisible, It was a remarkable insight, but it was purely theoretical. Nobody believed such objects actually existed. They were mathematical curiosities, thought experiments. When Karl Schwarzschild solved Einstein's equations in 1916, he found the same result, but now within the framework of general relativity. The Schwarzschild radius, the point of no return, became a real physical boundary. Yet even then, most physicists thought black holes were impossible. They believed that something must prevent such a complete collapse, some unknown quantum effect, some new physics. We now know that they were wrong. Black holes are not only possible, they are inevitable. They are the natural end state of any sufficiently massive star. They are the engines that power the most energetic phenomena in the universe, from quasars to gamma-ray bursts. They are the architects of galaxies, shaping the orbits of billions of stars from their dark thrones at the galactic centre, and they are the ultimate expression of gravity's dominion over matter. But let us return to the specifics of our solar system and the threat we face. Let us imagine for a moment that we had some warning. Let us say that a network of gravitational wave detectors, or perhaps a fleet of infrared telescopes positioned in the outer solar system, detected the black holes approach a century in advance. What would we do? What could we do? The answer is almost nothing. We could not deflect it. We could not destroy it. We could not hide from it. The only option would be to evacuate, to attempt to leave the solar system entirely. But this is not a simple proposition. The nearest star system, Proxima Centauri, is over 4 light-years away. We have never sent a human being farther than the Moon. We have never sent a probe beyond the heliopause with a trajectory that would reach another star in less than tens of thousands of years. The technology required to move an entire civilization, or even a small fraction of it, across interstellar distances does not exist. It may never exist. And even if we could build an ark, a generation ship, a world ship capable of carrying a few thousand people across the void, where would we go? Every star system in the galaxy has its own dangers. Every planet has its own potential for catastrophe. We would be fleeing from one threat into the arms of another, unknown threat. And then there is the question of who gets to go. If a black hole is coming and only a handful of people can escape, who decides? How do we choose? The politics of extinction are unimaginably brutal. Wars would be fought over a seat on the last ship. The rich would try to buy their way out. The powerful would try to commandeer the resources. The desperate would riot. Civilization would collapse long before the black hole arrived. We would destroy ourselves out of fear, out of greed, out of the simple, undeniable truth that most of us are going to die. And we know it. This is the hidden horror of the black hole threat. It is not just the physical destruction. It is the psychological destruction that precedes it. The knowledge that the end is coming, that it is inevitable, that there is no escape for the vast majority of humanity, would break us. We are not built to face our own extinction with calm and dignity. We are built to fight, to flee, to survive. And when there is no fight, no flight, no survival, we break. Consider the historical parallel of the Black Death in 14th century Europe. When the plague arrived, it killed perhaps a third of the population. Society did not respond with rational planning. It responded with panic, with scapegoating, with religious extremism, with the burning of Jews and witches, with the flagellants whipping themselves in the streets. And that was a threat that killed only a fraction of the population. Multiply that by 1 million. Multiply that by the entire species. The chaos would be absolute. But let us look beyond the human perspective. Let us look at the solar system itself. The black hole's approach would have a profound effect on the Sun. The Sun is a ball of plasma, held together by its own gravity and powered by nuclear fusion. As the black hole approaches, the Sun would begin to feel its gravitational pull. The Sun would start to deform, to bulge toward the black hole. This would disturb the delicate balance of forces inside it. The fusion reactions in the core might become unstable. The Sun could begin to pulsate, to flare, to eject massive amounts of material into space. These solar storms would be millions of times more powerful than anything we have ever observed. They would strip the atmospheres of the inner planets. They would boil the oceans. They would turn the Earth into a lifeless, scorched rock long before the black hole even reached us. The black hole would not need to touch us. The sun would do its work for it. And after the black hole passes, what remains? The solar system would be unrecognizable. The planets, if any survive, would be flung into new chaotic orbits. Some would be ejected entirely, becoming rogue planets drifting through interstellar space. Others would be captured by the black hole, becoming its new satellite system. The asteroid belt would be scattered, the Kuiper belt disrupted, the Oort cloud dispersed. The sun itself might be torn apart, its material feeding the black hole for thousands or millions of years, creating a brilliant accretion disk that would outshine every star in the galaxy. And then eventually, the feeding would stop. The black hole would move on, the accretion disk would fade, and there would be nothing left but a cold, dark void where a warm, living star system once existed. No monument, no record, no memory. The atoms that once made up your body, that once made up the trees and the oceans and the cities, would be scattered across the galaxy, some of them falling into the black hole, others drifting in the interstellar medium, perhaps eventually becoming part of a new star, a new planet, a new life. But the pattern, the information, the history, would be gone forever. Entropy wins. Order dissolves. The universe tends toward chaos, and black holes are the ultimate expression of that tendency. This is the final lesson of the black hole. It is not just a threat. It is a reminder. A reminder that everything we build, everything we love, everything we are, is temporary. The universe does not owe us permanence. It does not owe us meaning. We create our own meaning, our own permanence, in the brief flicker of time we are given, and when that flicker ends, it ends. But perhaps there is a strange comfort in this. If everything is temporary, then every moment is precious. Every sunrise, every conversation, every breath is a gift that will not come again. The black hole, in its silent, patient approach, teaches us to appreciate what we have, not because we can keep it, but because we cannot. We are all, in the end, on a one-way journey toward the event horizon. The only question is how we spend the time we have left. And so we look up at the night sky, and we know that somewhere out there, a black hole may be drifting toward us. Or it may not. We cannot know. We can only live, and love, and create, and hope that our brief existence matters, even if only to ourselves. Because in a universe of black holes and dying stars, our consciousness, our awareness, our ability to feel wonder and terror and joy is the rarest and most precious thing of all. The galaxy continues its silent dance. The black holes drift, the stars burn, and we, for a moment, are here. That is enough. That has to be enough, because there is nothing else. But of course, that peace, that quiet resignation, it's a fragile thing. Because the universe doesn't just have slow, grinding ways of ending things. It also has temper tantrums. And when the universe throws a tantrum, it does so on a scale that makes our sun's eventual death look like a candle flickering out in a hurricane. We've talked about the local threats, the things that are ours. But now we have to look outward. We have to look at the cosmic bullies. Because for all our talk about drifting black holes and dying stars, there is an event so violent, so utterly catastrophic, that it doesn't need to be in our neighbourhood to kill us. It just needs to be pointed in our general direction. We're talking about gamma-ray bursts, the most energetic explosions since the Big Bang itself. And I don't say that lightly. Think about every nuclear weapon ever detonated on Earth. Think about every fusion reaction happening inside every star in the Milky Way right now. A gamma-ray burst, in the span of a few seconds, can release more energy than our sun will produce in its entire 10 billion year lifetime. Let that sink in. Everything the sun has ever done, or will ever do, compressed into a single terrifying flash of light. That's the scale we're dealing with. These aren't just stellar events. These are stellar events that have been amplified by a factor of insanity. Now, nature, in its infinite variety, gives us two main types of these cosmic tantrums. The first is the long gamma-ray burst. These are the heavyweights. They're associated with the death of truly massive stars. stars that are at least 30 times the mass of our Sun. These aren't just supernovae, they are hypernovae. A hypernova is what happens when a star so massive collapses that it doesn't just explode. It creates a black hole on the spot, and the magnetic fields channel the infalling matter into two incredibly tight, focused jets. These jets shoot out of the star's poles at 99.9999% the speed of light. That is not a typo. We're talking about matter moving so fast that it feels like the universe should have a speed limit sign for it. And out of those jets comes the gamma radiation. Then you have the short gamma-ray bursts. These are the sucker punches. They don't come from the death of a giant star. They come from the merger of two neutron stars. Imagine two city-sized balls of nuclear matter, so dense that a teaspoon of their material weighs as much as a mountain, locked in a death spiral. They orbit each other, screaming through space, getting closer and closer until they finally touch. And when two neutron stars touch, they don't hug, they annihilate. The result is an immediate kilonova, and for a fleeting moment, a single gargantuan black hole is born. And again that birth screams out a beam of gamma radiation. The long bursts last for a minute or two. The short bursts last for less than 2 seconds. But in that time, they release the same amount of energy. The universe doesn't care about your sense of scale. And here's where it gets personal. Because these explosions don't throw their energy out in a big, friendly sphere like a supernova. They are focused. They are narrow. They are like the laser beam from a villain's lair in a cheesy movie. Except this laser is powered by the death of a star. What this means is that orientation is everything. For a gamma-ray burst to become Earth's problem, the business end of that cosmic ray gun has to be pointed almost directly at us. If the beam is off by just a few degrees, we get nothing. A silent, spectacular light show in a distant galaxy that our telescopes might catch. But if we are in the crosshairs, well, the term you'll hear a lot is the kill radius. For a typical gamma-ray burst, that kill radius is somewhere between 6,000 and 8,000 light-years. Let's unpack that. A light-year is about 6 trillion miles, so we're talking about a lethal blast zone that extends for 48 quadrillion miles. That is the range of a single bullet fired from a galaxy-sized gun. For context, the entire Milky Way galaxy is about 100,000 light-years across. So a gamma-ray burst could effectively sterilize a huge chunk of the galaxy. A bubble of space with a diameter of roughly 16,000 light-years. If it goes off within that bubble and is aimed our way. There are plenty of potential triggers inside that bubble, and if one of them goes off, the end doesn't take billions of years. It doesn't take millions of years. It takes about 10 seconds for the light to hit us from the edge of the kill radius. One moment we are here, the next moment the sky turns into death. So what does that moment actually look like? Let's walk through it, because it is the closest thing to biblical apocalypse that science can offer. First, the early warning systems. Satellites designed to detect nuclear weapons tests would see a flash, not from Russia, not from China, but from deep space. It would be a flash of gamma radiation so intense that it would momentarily blind the sensors. Astronomers would have about half a second to realize what it is. Then the atmosphere would light up. The gamma rays would slam into our upper atmosphere, smashing into nitrogen and oxygen molecules. This would create a secondary cascade of particles, a massive pulse of high-energy radiation that would bathe the planet. It would be like being inside a particle accelerator. The most immediate effect on the ground would be a visible flash. The entire sky would turn a brilliant, impossible blue-white. It would be 1,000 times brighter than the sun. Anything looking up would be instantly blinded. But blindness is the least of your worries, because the radiation is already doing its work. The gamma rays would rip through the ozone layer, not just damage it in a hole over Antarctica, but strip it away entirely. The ozone layer is our planet's sunblock. It is the shield that keeps the most dangerous ultraviolet radiation from reaching the surface. In a matter of minutes, that shield would be gone, vaporized. With the ozone gone, the UV light from our own sun becomes a sterilizing agent. The ultraviolet rays that would normally be blocked would now pour down onto the surface. Any life that was not shielded by deep water or thick soil would be cooked. The DNA in cells would be shattered. The molecules that make up life would be torn apart. The surface of the ocean, the top few meters, would become a sterile broth, and that is just the beginning. The gamma rays would also disrupt the atmospheric chemistry. They would break apart nitrogen molecules, causing them to combine with oxygen and form clouds of nitrogen dioxide. This brown, ugly smog would block out a significant portion of the sunlight. The world would grow dark and cold. Photosynthesis would grind to a halt. The base of the food chain, the phytoplankton in the oceans, would die. The plants on land, already scorched by the UV flash, would wither. Herbivores would starve. Carnivores would starve. It wouldn't be a quick death for everything. Some things would survive. Deep-sea vents, bacteria deep in the crust. But the world of complex life, the world of animals, of forests, of insects, of us, would be over. It would be a world that had been reset to a microbial state. And here's the chilling part. We have evidence that this has happened before. There is a theory, and it's a good one, that a gamma-ray burst caused the Ordovician extinction event roughly 450 million years ago. That was one of the big 5 mass extinctions. It wiped out about 85% of all marine species. The pattern of extinction fits perfectly. Fossils show a sudden loss of life in the shallow seas, where the UV would have been strongest, while deep-sea creatures were largely unaffected. The chemistry of rocks from that time shows a spike in certain isotopes that would be produced by a nearby cosmic explosion. We don't know for sure if it was a gamma-ray burst, but it is the best explanation we have. The galaxy has fired its gun before, and the bullet hit us. So are there any guns pointed at us right now? Are there any cosmic snipers in our neighbourhood? For a long time, there were 2 main suspects. The first was a star system called WR104. It is a Wolf-Rayet star, a massive, hot, dying star that is a prime candidate for a hypernova. It's located about 8,000 light-years away, right on the edge of our kill radius. And the terrifying thing was, when astronomers first looked at it, they thought its rotation axis was pointed almost directly at Earth. It looked like the barrel of a gun. For years, WR104 was the poster child for a potential doomsday scenario. People worried, people wrote books about it. But then, more precise measurements came in. Better telescopes, better models, and it turned out the threat was overblown. The axis is slightly tilted. If WR104 goes hypernova, the jet will likely miss us. Most astronomers now consider it a low threat, but you'll notice the word is low, not zero. The other big name was Eta Carinae. This is a monster of a star system, actually 2 massive stars locked in a chaotic dance. It's about 7,500 light-years away. It is unstable. It has already had massive eruptions, throwing off giant clouds of gas. For a while, people thought it was a hypernova waiting to happen, maybe even sending a gamma-ray burst our way. But again, the science has evolved. We now understand that Eta Carinae is probably not the right kind of star for a long gamma-ray burst. It's massive enough, but its spin and magnetic field aren't aligning in the necessary way. It will almost certainly go supernova one day and become a very impressive black hole, but it will probably do so without the terrifying laser beam effect. It was downgraded from a clear and present danger to a fascinating object of study. So, the snipers are not currently aiming at us, but the gun is still loaded. The universe is still full of possibilities. So what are the actual odds? What is the probability that our civilization, or any future civilization on Earth, will be wiped out by a gamma-ray burst? Well, the numbers are surprisingly high. Astronomers have calculated the rate of gamma-ray bursts in a galaxy like ours. They happen, on average, once every 10,000 years or so. Most are far away. Most are not aimed at us. But if you factor in the volume of our kill radius and the random orientation of these jets, the math gives a chilling result. There is roughly a 50% chance that a lethal gamma-ray burst will occur within about 500 million years. 500 million years. That sounds like a lot. It is a lot. It's longer than complex life has existed on land. But it is also a finite number. It is a deadline written into the physics of the galaxy. You could think of it as a coin flip. Heads, life continues to evolve. Maybe into something unimaginably brilliant, maybe into a spacefaring civilization that finally says goodbye to its cradle. Tails, the sky flashes, the ozone disappears, and the planet is returned to the realm of microbes. It is a statistical certainty that given enough time, the coin will come up tails. And what is beautiful and terrifying about this scenario is that the planet itself is largely unaffected. The gamma ray burst is not a physical impact. It doesn't shatter the crust. It doesn't boil the oceans away. It doesn't even rattle the continents. The sun still shines. The Earth keeps spinning. The geology is fine. The atmosphere eventually settles down after a few decades, a century at most. The planet survives. But everything on the surface, everything that built cities and wrote poems and wondered about the stars, all of that is erased. From the perspective of a civilization, that is total destruction. There is nothing left to rebuild. You are not a species in the aftermath of a war, digging through rubble. You are a species that has been turned into a fossil layer. Your skyscrapers stand, empty and sterile, for a few thousand years before they crumble. Your books, your art, your digital records, they are all cooked by the UV light before the darkness sets in. Even if small pockets of life survive, deep in caves or under the ocean floor, the thread of human consciousness is broken. It is not a gradual decline. It is a sharp, violent, instantaneous end. You are here, and then you are not. So, as we stare up at the night sky, we are not just looking at beauty, we are looking at potential threats. Every supernova in a nearby galaxy is a reminder that the universe is a violent place. Every collision of neutron stars that we detect with our gravitational wave observatories is a reminder that the most powerful forces in the cosmos are utterly indifferent to our existence. We live on a speck of dust in a shooting gallery, and while the odds are in our favour for the immediate future, the long-term odds are a coin flip. We started this journey talking about the quiet end of the sun. That was a slow, predictable tragedy. This is the sudden heart attack. This is the universe deciding that it is done with you, and there is nothing you can do to stop it. No space program, no deflection mission, no planetary shield. You just have to hope the angle is off by a few degrees. You have to hope that the bullet misses. Because if it doesn't, the story of Earth, the story of life, the story of consciousness, it just stops, and the galaxy continues its silent dance. The black holes drift, the stars burn, and we for a moment were here, that is all. We tend to think of the solar system as a clock, a perfect, silent, celestial machine. The planets spin, the sun burns, and everything will tick along just fine until the sun runs out of hydrogen and expands into a red giant, swallowing Mercury, Venus, and maybe Earth billions of years from now. That's the story we tell ourselves to sleep at night. There is a deadline, sure, but it's so far away we can treat it like it doesn't exist. It's a false sense of security, a comforting lie. Because the truth is, the solar system is not a clock. It's more like a game of billiards played on a table that's slowly tilting, with players who keep nudging the table when you're not looking. And the balls, those are worlds. The end could come much, much sooner than we think. Not from the sun's death, but from the silent, grinding chaos that lives right under our feet. Or rather, right under our orbits. Let's start by challenging this illusion of long-term stability. We have this idea that the orbits of the planets are fixed, eternal. They've been looping around the sun for 4.5 billion years, so why would they change now? But here's the kicker. The solar system is not an isolated system. It's a busy, messy, gravitational swampland. Every planet pulls on every other planet. Every asteroid, every comet, every speck of dust exerts a force however tiny. And these tiny forces over millions of years add up. This is the domain of orbital chaos, and the man who mapped it out is a French mathematician named Jacques Lascar. He ran simulations, thousands of them, and he found something terrifying. The solar system is not stable over geological timescales. In fact, we cannot predict the positions of the planets beyond about 5 million years with any real confidence. Think about that. 5 million years. That sounds like a lot, but in the context of Earth's history, it's barely a blink. dinosaurs were wiped out 66 million years ago. So, if you were to fast forward the solar system a few tens of millions of years, the planet's orbital paths start to look like a scribble on a piece of paper being shaken by an earthquake. Why does this happen? It's because of resonances. Imagine a child on a swing. If you push them at exactly the right moment, they go higher. If you push them at the wrong moment, they slow down. The planets do the same thing, but with gravity. Jupiter and Saturn have a famous resonance pattern. They align in a specific way every few hundred years, and that alignment gives a subtle gravitational shove to the inner planets, especially Mercury. And here's where it gets personal for Earth. Mercury is the loose cannon. It's the smallest planet, the closest to the Sun, and its orbit is already eccentric. It's a bit stretched out, like a tilted oval, and because it's so small and so close to the Sun's immense gravity, it's the most susceptible to these tiny, chaotic nudges from the gas giants. Laska's simulations showed that Mercury has about a 1% chance of going completely haywire within the next 5 billion years. That's a 1 in 100 chance that the smallest planet in the inner system will either slam into the Sun, crash into Venus, or be thrown entirely out of the solar system. But here's the nightmare scenario. It doesn't have to hit Mercury for it to be the end of the world. If Mercury's orbit becomes chaotic, it can cross the path of Mars. Then Mars gets nudged. And then Mars, with its larger mass, can disrupt Earth's orbit. It's a cascade, a slow-motion car crash that takes millions of years to unfold, but once it starts, it's unstoppable. One simulation showed that a chaotic Mercury could eventually fling Earth right into the Sun, or eject us into the cold void of interstellar space. Imagine that. Earth, the blue marble, the only known home of life, just drifting away from the Sun, the oceans freezing solid, the atmosphere bleeding out, all because a little rock the size of our moon got bumped a few thousand kilometers off its path a billion years ago. That's chaos. That's the false limit of our long-term stability. But wait, there's another player lurking at the edge of the system. A hypothetical giant. Something that could turn this slow-burn chaos into a targeted catastrophe. I'm talking about Planet 9, not Pluto. Pluto is a snowball compared to what might be hiding out there. For years, astronomers have noticed something weird about the Kuiper belt, that icy ring of debris beyond Neptune. The orbits of several distant objects are strangely clustered. They all tilt the same way. They all have similar eccentricities. Statistically, this alignment should be incredibly rare. It's like finding a bunch of marbles all rolling into the same corner of a table for no reason. The most likely explanation: a massive unseen planet is herding them. This theoretical world, sometimes called Planet 9, is thought to be a super-Earth, about 5 to 10 times the mass of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units. That's 400 to 800 times the distance between Earth and the Sun. To put that in perspective, it's so far out that a single orbit around the Sun could take 10,000 to 20,000 years. It would be incredibly faint, a dim dot moving so slowly that it could take decades of observations to confirm its existence. We haven't seen it yet, but the evidence is mounting, and if it exists, it's not just a quiet neighbour, it's a weapon. Here's the thing about Planet 9. Because it's so massive and so far out, it exerts a gentle but persistent gravitational influence on the entire outer solar system. It pulls on comets and asteroids in the Kuiper belt and the Oort cloud, that vast spherical shell of icy bodies that surrounds the Sun at a distance of up to 100,000 astronomical units. Normally, these icy bodies just sit there, frozen, for billions of years. But Planet 9 acts like a cosmic shepherd. It can tilt their orbits. It can nudge them. And once it nudges them just right, gravity from passing stars or the galactic tide can finish the job, sending a comet screaming into the inner solar system. Planet 9 is a comet gun. A slow, patient, remorseless gun. Every 10 million years or so, it may cause a spike in the number of long-period comets that swing past Jupiter and head straight for the inner planets. And some of those comets hit Earth. Now, here's where the story gets even stranger. Scientists have noticed a pattern in Earth's history. Major extinction events, The big ones seem to occur every 27 million years or so. The Cretaceous Paleogene extinction that wiped out the dinosaurs? That was 66 million years ago. The Permian-Triassic extinction, the Great Dying, was about 252 million years ago. That's a gap of about 186 million years, which is not exactly 27 million, but if you look at the smaller extinction pulses, there's a suspicious regularity. Some researchers think this cycle is linked to the Sun's motion through the Milky Way. As the solar system bobs up and down through the galactic plane, it encounters denser regions of gas and dust that can disturb the Oort cloud. But others, like Michael Brown and Konstantin Batygin, the astronomers who proposed Planet 9, have suggested that this 27 million year extinction cycle could be directly tied to the orbit of Planet 9. As Planet 9 slowly precesses, or wobbles on its own orbit, it might periodically send a barrage of comets our way. Every 27 million years, the gun fires, and we're sitting in the middle of the target range. But let's be honest, we don't know for sure. There's another hypothesis that says the clustering of Kuiper Belt objects isn't caused by a planet at all. It could be caused by a massive tilted disk of icy debris. A collective mass, maybe tens of Earth masses, spread out in a ring at the edge of the solar system. This disk could create the same gravitational effect as a planet, but it would be much harder to detect. It would be like trying to see a swarm of dark snowflakes from a distance of 500 astronomical units. The point is, whether it's a single super-Earth or a disk of thousands of frozen worlds, the outer solar system is not empty. It's not a vacuum. It's a reservoir of potential destruction, and we are at the mercy of whatever lurks out there. Even if Planet 9 doesn't exist, even if the Kuiper disk turns out to be a mirage, there's another slow, inevitable force that will eventually tear the solar system apart. The galactic tide. Think of it like this. The Sun and its planets are orbiting the centre of the Milky Way. Every time we pass through the galactic plane, we feel a gravitational tug from the dense matter there. It's not strong, not on our timescale, but over billions of years, it steadily erodes the Oort cloud. It pulls comets out of their long, lazy orbits. Some of them fall toward the Sun. Some are flung out into the void. The Oort cloud is not a permanent feature. It is slowly dissolving, like a cloud of smoke in a drafty room, and as it dissolves, the number of long-period comets that can hit Earth will decrease. That sounds good, right? Fewer comets. But the flip side is that the solar system is losing its protective halo. The Oort cloud acts as a buffer, absorbing some of the gravitational shocks from passing stars. As it thins out, the planets become more exposed, more vulnerable, and eventually the galactic tide will do more than just nudge comets. It will start to pull the planets themselves. Over tens of billions of years, long after the Sun has died, the solar system will loosen its grip. Planets will drift away, one by one, until only the Sun remains. A cold, dead ember surrounded by nothing. So the false limit is this idea that everything is fine until the Sun expands. It's a comforting thought, but it's a lie. The solar system is a chaotic, violent, and temporary arrangement. It could end next week because of an undetected comet. It could end in 100 million years because Mercury goes rogue and sends Earth into the Sun. It could end because Planet 9, that hidden spectre, decides to start a new extinction cycle. Or it could end because the galactic tide slowly pulls everything apart. The only constant is change, and the only certainty is that our sense of security, our belief that we have billions of years to figure things out, is an illusion. We are standing on a fragile orb, spinning through a cluster of gravitational booby traps, and we have no idea when the next one will go off. You see, this is the real lesson. Not that we are doomed. That's too simple. The real lesson is that we are on a journey. The solar system is not a static museum. It's a dynamic living system that is constantly being reshaped by forces we barely understand. And we, as a species, have only been watching for a few thousand years. That's less than a blink in the cosmic timeline. We don't know what's coming. We don't know if Planet 9 is real. We don't know if Mercury will stay in its lane. We don't know when the next big comet will hit. But we do know this. The clock is ticking. And it's not set to the sun's death. It's set to the chaos of the universe. The false limit is the belief that we are safe. The truth is, we never were. And that's not depressing. That's liberating. It means we have to pay attention. We have to keep looking. We have to keep asking questions. Because the solar system is not done with us yet. Not by a long shot. And the next act of this story might be written in the skies above us, or in the dark, silent depths of the Oort cloud, where something ancient is stirring. We just have to be watching when it does. And the most unnerving part of this entire equation is how late we started looking. For the vast majority of human history, the sky was a static canvas, a dome. The stars were fixed points of light, and the planets were wandering stars with predictable paths. We mapped them, we named them, we built calendars around them, but we never considered them dangerous. The idea that the heavens could reach down and snuff out civilization was a religious concept, a punishment from God. It wasn't a geological fact. It wasn't an astronomical reality. We were blind. And we stayed blind until the late 20th century, when a group of astronomers finally decided to look for the killer. In 1980, Luis Alvarez and his son Walter proposed that a massive asteroid impact had caused the extinction of the dinosaurs. It was a radical idea. It was met with ridicule. Scientists had assumed that extinction events were slow, gradual affairs, driven by climate change or volcanic eruptions. But the Alvarez team found a layer of iridium, a metal common in asteroids but rare in Earth's crust, laid down exactly 66 million years ago. It was the smoking gun, and suddenly the sky became a threat. The threat was real, the threat was statistical, and the threat was overdue. If the extinction of the dinosaurs was caused by a 10-kilometre-wide asteroid, then an event of that magnitude happens about once every 100 million years. That means the next one is statistically due, not tomorrow, but within a geological instant. And here we are, a species that has only existed for 300,000 years, completely unaware that the ground beneath our feet has been hit billions of times before. We are walking on a graveyard of impacts. But size isn't everything. The real danger is the one we cannot see, the one that comes from the wrong direction. Our current asteroid detection systems are focused on the main belt between Mars and Jupiter, and the near-Earth objects that cross our orbit. We track them, we catalogue them, we calculate their trajectories, but we are only looking at a tiny fraction of the threat. Most of the comets in the Oort cloud, the icy bodies that live at the edge of the solar system, are completely invisible to us. They are dark, they are cold, they could be heading our way at speeds of 50 kilometers per second, and we wouldn't know until they passed the orbit of Jupiter, which gives us, at most, a few years of warning. And a few years is not enough. Not for a civilization that has never built a planetary defense system, not for a civilization that cannot agree on climate change. The threat is not just the rock. The threat is our own incompetence, and this brings us to the most terrifying scenario of all. A scenario that bypasses rocks and comets entirely. A scenario that is written in the fabric of gravity itself. Imagine a star, any star. The closest star to us is Proxima Centauri, about 4.2 light-years away. That sounds impossibly far, but the galaxy is moving. Everything is moving. The Sun is orbiting the galactic centre at a speed of 220 kilometers per second. Other stars are moving too, and every now and then a star passes close enough to the solar system to disturb the Oort cloud. Not a collision, just a passing. A gravitational nudge. This has happened before. About 70,000 years ago, a dim red dwarf called Schultz's star passed through the outer Oort cloud, coming within 52,000 astronomical units of the Sun. That's close, in astronomical terms. It was a near miss, and it sent a ripple through the cloud, sending a shower of comets inward. That shower hasn't reached us yet. It's still on its way. Some of those comets will arrive in the next few 100,000 years. They are already heading toward the inner solar system. We just don't know when they'll arrive. And this is the quiet misery of our existence. We are not masters of this system. We are passengers. We are passengers on a ship that is sailing through a minefield, and we are only just now beginning to realize that the captain is drunk, The maps are wrong, and the hull is made of paper. The false limit of long-term stability is the belief that the sun's death is the only deadline. It is not. The solar system could be reshaped by a passing star in 100,000 years. It could be shattered by a rogue planet in 1,000,000 years. It could be sterilized by a gamma ray burst from a nearby supernova in 1,000 years. We have no control. We have no plan. And the worst part is that we are not even looking in the right place. Consider the Voyager probes. They were launched in 1977. They are now the most distant human-made objects in existence. They are leaving the solar system. And what have they found? A boundary. A place where the sun's influence gives way to the interstellar medium. They have found that the edge of the solar system is not a gentle fade. It is a turbulent, chaotic region full of magnetic bubbles and energetic particles. It is a storm, and beyond that storm there is a void that contains the remnants of other stars, a void that contains the debris of other systems. The solar system is not an island. It is a leaky boat in a dangerous sea, and the leaks are getting worse. So what does this mean for us? It means that the clock is not just ticking for the sun. The clock is ticking for the entire system. Every second the orbits of the planets are shifting. Every second the Oort cloud is being eroded by the galactic tide. Every second the chance of a passing star increases. We cannot stop any of this. We can only understand it. And understanding it means accepting that we are living in a temporary arrangement. The solar system as we know it is a fleeting configuration. It has existed for 4.5 billion years, but it will not exist for another 4.5 billion years. It will change. It will break. And one day it will be unrecognizable. But here is the strange paradoxical hope. The false limit is also an invitation. It is an invitation to grow up, to stop pretending that we have forever, to stop treating the Earth as an infinite resource, to stop ignoring the sky. We have the technology to detect threats. We have the physics to deflect them. We have the mathematics to predict chaos. But we lack the will. We lack the urgency. We lack the collective imagination to see beyond the next election cycle. The false limit of long-term stability has lulled us into a stupor, and the only cure is to look up, to accept that the universe is not safe. It never was, and it never will be. The end of the solar system is not a single event, it is a process, and we are in the middle of it. The only question is whether we will be awake for the rest of the journey, or whether we will sleep through the whole thing, right up until the moment the sky catches fire. And so we arrive at the true limit. Not a single event, not a flash of light or a final scream of gravity, but a synthesis, a slow grinding convergence of every possible end compressed into one final truth. The solar system will not die in a single way. It will die in every way that the universe can offer, and the only thing that matters is which one gets there first. Let me walk you through the logic of this ultimate fate. For the vast majority of scenarios, the sun's death will dominate. It is the most predictable, the most certain, the one thing we can set our clocks by. In about 5 billion years, our star will exhaust the hydrogen in its core. It will swell into a red giant, swallowing Mercury, Venus, and probably Earth. Mars will become a scorched cinder. The asteroid belt will be vaporized. The gas giants will be heated beyond recognition, their atmospheres stripped away, their moons turned to dust. This is the default end. This is what happens if nothing else intervenes. But here is the problem. The universe is not a clockwork machine. It is a chaotic, violent, random place, and sometimes something else gets there first. Consider the possibility of a stellar flyby. A rogue star drifting through the galaxy for billions of years could one day cross paths with our sun. It does not need to hit us. It just needs to get close. And when I say close, I mean within the Oort cloud, a distance of about 1 light year. At that distance, the gravitational pull of this passing star would be enough to destabilize the entire system. Comets would be flung inward, planets torn from their orbits, the entire delicate architecture of the solar system scrambled like a deck of cards thrown into a hurricane. This is not science fiction. This is statistics. The galaxy is thick with stars, and over billions of years, the probability of a close encounter is not zero. It is a matter of when, not if. And then there is the black hole. A wandering black hole, a remnant of some ancient supernova, drifting through the void. It could pass through the outer reaches of the solar system, and the result would be immediate and catastrophic. The black hole would not need to swallow the sun whole. Its gravity alone would be enough to rip the planets apart. Tidal forces would shred Earth, the Moon, Mars into streams of gas and debris. The sun itself would be distorted, its outer layers pulled into an accretion disk around the black hole. Then, slowly, over thousands of years, the entire system would be consumed. The sun would be stretched into a long glowing thread, and then that thread would vanish into the event horizon. Gone, as if we had never existed. But there is an even faster end, a gamma-ray burst. A narrow beam of pure energy, focused like a cosmic laser, erupting from a collapsing star thousands of light years away. If that beam swept across the solar system, we would not have time to register what was happening. The atmosphere would be stripped away in seconds. The oceans would boil. The surface of every planet would be sterilized. The sun itself would be unaffected, but everything orbiting it would be dead. The solar system would become a shell, a ghost, a collection of barren rocks, circling a star that no longer has anything to care for. So which one is it? Which end will actually happen? The answer is that we do not know, and that is the point. The solar system is not a story with a single ending. It is a branching tree of possibilities, and the branch we end up on depends on the randomness of the universe. The only thing we can say for certain is that the sun will die, but when it does, the solar system will already be a very different place. Let us look at the most likely outcome. After 10 billion years, give or take a few billion, the sun will have become a white dwarf, a dense, Earth-sized ball of carbon and oxygen, glowing faintly with residual heat. It will no longer produce energy through fusion. It will simply cool, slowly, over trillions of years, and around it, the remnants of the solar system will still orbit, but they will be frozen. The outer planets, Jupiter, Saturn, Uranus, Neptune, will have drifted outward, their orbits expanding as the sun lost mass. They will be dark, cold, dead worlds. Their atmospheres will have frozen and fallen to the surface. Their moons will be silent. The asteroid belt will be a sparse collection of rubble, scattered and broken. The Kuiper belt will be thin, most of its objects ejected by gravitational interactions. And the Oort cloud, that vast sphere of comets surrounding us at a distance of nearly a light year, will be mostly stripped away. Stellar flybys will have torn it apart, scattering its contents across the galaxy. The solar system will be a skeleton, a ghost of its former self. But that is not the end, because the galaxy itself is changing. The Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will begin to merge. The solar system, if it still exists at that point, will be flung into a new environment. It could be ejected entirely, cast out into intergalactic space, where it would drift forever in the dark. Or it could be pulled into the centre of the new galaxy, where it would be torn apart by the supermassive black hole that lurks there. Or it could simply be scattered, the sun and its white dwarf remnant flying off in one direction, while the planets are pulled away into different orbits around different stars. The solar system as a coherent structure will cease to exist, and even if it survives the merger, even if it drifts alone in the void, there is another end waiting. A much, much slower end. The end of the protons themselves. This is where the story becomes truly strange. Because if the theories of grand unification are correct, then protons are not stable. They decay. It is an incredibly slow process. The half-life of a proton is estimated to be around 10 to the 34th years. That is a 10 with 34 zeros after it. To put that in perspective, the current age of the universe is about 13.8 billion years, which is 10 to the 10th years. So proton decay is a process that takes 10,000 trillion times longer than the current age of the universe. It is so slow that we cannot even be sure it happens, but if it does, then even the white dwarf itself will eventually disappear. The carbon and oxygen atoms that make up the sun's corpse will slowly, one by one, fall apart. Their protons will decay into positrons and other particles. The white dwarf will lose its mass, becoming a cloud of dissipating energy. And then, after another unimaginable stretch of time, even those particles will decay. The solar system will become nothing, a memory that never existed, a pattern that has been erased. But here is the thing. That is not the end of the solar system. That is the end of matter itself. The solar system ceased to be a recognizable entity long before that. It ended when the sun became a white dwarf. It ended when the planets were frozen or ejected. It ended when the Oort cloud was stripped. It ended when the galaxy merged and scattered the pieces. The proton decay is just the final academic footnote. The solar system is gone. What remains is a collection of atoms that used to be something, drifting in a universe that is becoming increasingly empty. And that is the true limit, the interplay of randomness and entropy. The solar system will not simply fade. It will be torn apart, burned, or scattered by forces we are only beginning to understand. There is no gentle twilight. There is no slow, dignified decline. There is only the grinding chaos of a universe that does not care about our little corner of it. So what does this mean for us? For the humans who are reading this or watching this or listening to this right now? It means that we are living in a moment of profound rarity. The solar system is young. It is vibrant. The sun is still burning bright. The planets are still in their orbits. The Oort cloud is still intact. And we are here to witness it. We are the lucky ones. We are the ones who get to see the solar system in its prime before the inevitable decay sets in. And that is a gift. A strange, terrifying, beautiful gift. But it is also a responsibility. Because if we are going to understand the end, we have to understand the beginning. We have to understand the forces that shape our universe, the probabilities that govern our existence, the randomness that will one day tear it all apart. And we have to accept that we are not in control. We never were. The solar system is not a machine we can fix. It is a wild, untamed thing, and it will end in ways we cannot predict. So the next time you look up at the night sky, remember this. Every star you see is a potential killer. Every comet is a potential disruptor. Every black hole is a potential devourer. The universe is not safe, it never was. And it never will be. The end of the solar system is not a single event. It is a process. And we are in the middle of it. The only question is whether we will be awake for the rest of the journey, or whether we will sleep through the whole thing, right up until the moment the sky catches fire. But to truly understand this death, we must look back at what we have lost. We must understand the history of this place, the life it has harboured, the dreams it has inspired, because only then does the end have any meaning. The solar system is not just a collection of rocks and gas and ice. It is a stage, and for a brief flickering moment, it was a stage for life. Consider the Earth. For 4.5 billion years, this planet has been a crucible. It has seen continents rise and fall, oceans form and evaporate, ice ages come and go. It has witnessed the emergence of life, from the first single-celled organisms in the primordial soup, to the complex multicellular creatures that crawled onto land, to the dinosaurs that ruled for 165 million years, to the mammals that scurried in their shadows to us. We are the latest product of this long, unbroken chain of evolution. We are the ones who looked up at the stars and wondered what they were. We are the ones who built telescopes and spacecraft, who sent probes to every planet, who walked on the moon. We are the ones who began to understand the cosmos, and in doing so, we began to understand our own fragility. But that fragility is not just ours, it is the fragility of everything we have ever known. The history of human civilization, from the first cities in Mesopotamia to the global network of the 21st century, is a story written on a planet that will one day be vaporized. Every painting, every symphony, every poem, every scientific discovery, every act of kindness and every act of cruelty, every love and every hate, every memory and every dream, all of it will be erased. Not in 1 billion years. Not in 1 trillion years. In 5 billion years, give or take a few hundred million. And that is a sobering thought. But let us be more precise. Let us look at the timeline of this destruction, because it is not a single clean event. It is a cascade. The sun will not simply explode. It will transform. In about 1 billion years, it will already be 10% brighter than it is today. That might not sound like much, but it is enough to trigger a runaway greenhouse effect on Earth. The oceans will begin to boil. The atmosphere will thicken with water vapor, trapping more heat, accelerating the process. In a few 100 million years, the Earth will become a Venus-like world, a hellish, pressurized furnace, with a surface temperature of hundreds of degrees Celsius. The last traces of life will vanish, the rocks will melt, the oceans will become steam, and that is just the beginning. The planet will still be there, but it will be a sterile, lifeless rock, circling a star that is slowly killing it. Then, in about 5 billion years, the Sun will run out of hydrogen in its core. It will begin to fuse helium, and in doing so, it will swell. It will become a red giant, and its outer layers will expand to engulf the inner planets. Mercury will be the first to go, vaporized in a matter of hours. Venus will follow, its atmosphere stripped away, its surface turned to liquid rock. And then Earth. The Earth will be consumed. Not in a flash, but in a slow, inexorable embrace. The Sun's outer layers will reach the orbit of Earth, and the planet will be dragged through the stellar atmosphere. It will burn, it will break apart, it will become part of the Sun itself. The iron core of our planet, the very heart of our world, will be dissolved into the star's interior. The Earth, the only home we have ever known, will cease to exist. It will be a memory that only we carry, and soon we will carry it no longer. But the outer planets will survive for a time. Jupiter and Saturn will be heated, their atmospheres stripped, their moons melted. They will be scarred, broken, but they will still orbit. And then the Sun will shed its outer layers. It will become a planetary nebula, a beautiful expanding cloud of glowing gas. And in the centre of that nebula, there will be a white dwarf, the core of our star, a diamond in the sky. And that white dwarf will be the gravestone. It will mark the spot where the solar system once lived. It will shine faintly for trillions of years, and around it the frozen remnants of the outer planets will circle in the dark. Jupiter, Saturn, Uranus, Neptune, their orbits slowly expanding as the Sun lost mass, will become cold, dead worlds. Their atmospheres will have frozen and collapsed onto their surfaces. They will be dark, silent, airless. Their moons will be the same. Europa, with its subsurface ocean, will be a ball of ice, locked solid. Enceladus, with its geysers, will be a frozen statue. Titan, with its methane lakes, will be a nitrogen ice desert. All of them dead, all of them silent, and then the real waiting begins. Because the white dwarf will not last forever. It will cool slowly, over trillions of years. It will fade from white to yellow to red to infrared to microwave. Eventually, it will become a black dwarf, a cold, dark, Earth-sized lump of crystallized carbon, and it will orbit the galactic center, dragging its frozen family with it for a time. But the galaxy is not static. Over the next few billion years, the Milky Way will collide with Andromeda. The solar system, if it is still intact at that point, will be caught in the chaos of this merger. It could be flung away from the galactic center, sent adrift in intergalactic space. It could be pulled in, drawn toward the supermassive black hole at the center of the new galaxy, where it would be torn apart by tidal forces. Or it could simply be scattered, the white dwarf and its planets each flying off in different directions, lost to the void. The last trace of the solar system, the white dwarf itself, will become a rogue star, a wanderer in the darkness between galaxies, and there it will continue to cool. For trillions upon trillions of years, it will drift through the void alone. It will pass through the emptiness of intergalactic space, where there are no stars, no planets, no light. It will be a cold, dark ember, a fossil of a star that once gave life to a world, that once gave birth to a civilization, that once looked up at the stars and wondered. And then, if the theories are correct, the protons will decay. The white dwarf, which is made of carbon and oxygen, will begin to dissolve. It is a process so slow that it is almost incomprehensible, but it is relentless. Over 10 to the 34th years, the protons in the white dwarf will decay into positrons and other particles. The white dwarf will lose mass. Its structure will crumble. It will become a cloud of dissipating energy, a faint glow in the darkness, and then nothing. The last remnant of the solar system, the last physical trace of our sun, our Earth, our civilization will be gone. But even that is not the end, because the universe itself is dying. The expansion of space is accelerating. Galaxies are moving away from each other. Eventually they will be so far apart that light will not be able to travel between them. The universe will become a vast, cold, empty void with only the most resilient forms of matter surviving. And then, even those will decay. Black holes will evaporate through Hawking radiation. Matter will become energy, and energy will become nothing. The universe will reach a state of maximum entropy, a state of perfect eternal equilibrium, the heat death of the cosmos, and in that end, even the memory of the solar system will be erased. There will be nothing to remember it by. No records, no fossils, no light. The solar system will have ended, truly ended, not in a single cataclysm, but in a slow, grinding dissolution that takes longer than anything we can comprehend. So what do we do with this knowledge? What do we do with the fact that everything we love, everything we have built, everything we are, will one day be gone? We do what we have always done. We live, we love, we create. We learn, we explore, we leave something behind. We send probes to the stars. We write our history in the magnetic domains of objects that will outlast us. We build civilizations on other worlds. We become a multi-planet species, then a multi-star species, then a species that spans the galaxy. We fight against the darkness, not because we can win, but because that is what it means to be alive. Because in the end, the solar system is not a destination. It is a starting point. It is the cradle from which we will one day soar. And even if the cradle is destroyed, even if the sun dies and the planets crumble and the atoms decay, we will have already left. We will have taken the memory of this place, the memory of Earth, the memory of the stars, with us, and we will carry it into the future, into the darkness, into the unknown. And that is the real end of the solar system. Not when the sun becomes a white dwarf, not when the Earth is vaporized, not when the protons decay. The solar system ends when the last thing that remembers it is gone. And as long as we are here, as long as we remember, the solar system is not dead. It lives on in us, in our stories, in our dreams, in our children. And that is the only victory we can ever hope for. That is the only meaning we can ever create. That is the limit we have reached. And beyond that limit, there is only the silence of the cosmos, waiting for us to fill it with our song. We have reached the edge of something here, not just the edge of our solar system, not just the cold boundary where our sun's influence fades into the black, but the edge of our own understanding. And it is time, I think, to turn around, to look back, to bring this vast cosmic story home to the one place it truly matters, right here, inside your own chest, beating with the rhythm of a heart that was born from stardust. Because here is the thing we so often forget, the thing that makes this whole journey both humbling and deeply, profoundly beautiful. Every single atom in your body, every iron molecule in your blood that lets you breathe, every calcium atom in your bones that holds you upright, every speck of carbon that forms the very fabric of your being. It was all forged in the heart of a star that lived and died, long before our sun was even a flicker of light in the cosmic nursery. You are not just a person living in the universe. You are the universe. You are a way for the cosmos to know itself, to feel itself, to question its own existence. And the same cosmic forces that gathered that stardust together, that spun it into a planet, that nurtured life through eons of chaos and ice and fire, those same forces will one day take it all apart. But let me ask you something. Does that make you sad? Does that make this moment, right now, any less precious? When you think about the heat death of the universe, or the eventual white dwarf that our sun will become, does it make the laughter of a child, or the warmth of a loved one's hand any less real? No, of course it doesn't. It does the exact opposite. It makes every single second sacred. It makes the fact that you are here, breathing in a stable, warm, life-giving moment in the middle of a 4 billion-year story, nothing short of a miracle. Think about that stability for a second. We live in what astronomers call the habitable zone, the so-called Goldilocks region of our solar system, where water can exist as a liquid, where the atmosphere is just thick enough. where the magnetic field protects us from the solar wind. But more than that, we live in a rare, fleeting period of cosmic stability. The sun is middle-aged. It is calm. It is predictable. The asteroid belt has settled down. The gas giants have finished their violent migration. For a few 100 million years, maybe a billion more, the solar system is home. It is comfortable. It is the quiet before the storm. And we are the lucky ones who get to witness it. This is the cosmic perspective. And it is not about despair. It is about gratitude. It is about looking up at the night sky and understanding that every single one of those pinpricks of light is a story, a beginning and an end. It is about understanding that our own story, the story of humanity, of our children, of our dreams, of our civilizations, is written on a page that will eventually turn. But that does not mean the book is worthless. It means the book is precious, precisely because it has an ending. And so, when we talk about every way the solar system can end, from the slow freezing death of the red giant phase to the violent disruption of a rogue star tearing through our neighbourhood, we are not talking about tragedy. We are talking about nature. We are talking about the cycle. Stars are born, stars live, stars die. Planets form, planets are destroyed, life emerges. Life thrives, life fades, and the cosmos, the great indifferent machine that it is, just keeps on spinning. It does not mourn, it does not celebrate, it simply is. But we get to do the mourning, we get to do the celebrating, we get to feel the weight of it all. That is our gift, that is why we are here, and that is why understanding our eventual demise is not a macabre obsession. It is the deepest possible expression of our humanity. When you know that the sun will one day swell and swallow our world, you stop taking the sunrise for granted. When you know that the Andromeda galaxy is barreling toward us at 400,000 miles an hour, you stop taking the peaceful spiral of the Milky Way for granted. When you know that even the longest-lived stars will one day fade to black, you stop taking the very existence of light for granted. We are so small, we are so fragile. A single gamma ray burst from a distant supernova could strip our atmosphere in an instant. A single dark matter particle interaction could destabilize the very fabric of our nuclear forces. We are living on a thin crust of rock, suspended in a freezing vacuum, surrounded by chaos. And yet, we write poetry, we fall in love, we build telescopes to look back at the dawn of time. We send robots to the surface of Mars. We create music that echoes through the ages. We are a paradox. We are insignificant and magnificent all at once, and that is the most human thing of all. So here is my call to you. If this journey through the solar system's possible ends, through the fires and the freezes, through the collisions and the quiet fade-outs, if any of it has inspired you, if it has made you look at the night sky just a little bit differently, then do not let that feeling fade. Subscribe to This Is Space. Join us week after week as we keep exploring the universe's most profound questions. We will talk about the birth of galaxies. We will talk about the death of black holes. We will talk about the search for life on distant worlds. We will ask the hard questions together, because that is what we do here. That is what this community is about. I am Christopher, and remember, always remember, the cosmos is changing. It has been changing for 14 billion years. It will keep changing for trillions more. Nothing is permanent, nothing is safe, but that does not mean we give up. It means we look closer, we ask harder, we love deeper. Because we are made of stardust, and stardust has a voice, and that voice is ours. And so, let us close with a final image. A haunting one, I admit, but a beautiful one. The sun has died, it has swollen, it has raged, it has thrown its outer layers into the void, leaving behind only its core. A white dwarf. A tiny brilliant diamond of compressed carbon and oxygen, no larger than the Earth, but with the mass of an entire sun. It glows with a dying heat, a last ember of the fire that sustained us for billions of years, and it drifts, alone, through the interstellar void, past the ghostly remnants of the planets it once ruled. It drifts through the silence, carrying no life, no warmth, no memory of the world that once circled it. It is a tombstone. It is a monument. It is the last light of our home. And in that light, in that lonely fading glow, there is a story, our story. A story of a brief, beautiful moment when the cosmos woke up and said, "I am here." And it mattered, but let us sit with that image for a moment longer, because the white dwarf is not truly the end. It is a transition, it is a pause. Over the next trillion years, that brilliant diamond will slowly, almost imperceptibly, cool. The heat that remains, the last whispers of nuclear fusion that once roared at the core of our sun, will radiate away into the black. The white dwarf will become a black dwarf, a cold, dark lump of crystallized carbon, invisible to any instrument, floating through an increasingly empty universe. It will be a ghost, a memory made of matter, waiting for something that will never come. And around it, if anything remains, there will be the debris of the solar system. The gas giants, perhaps, stripped of their atmospheres, their cores exposed as frozen, rocky worlds. The asteroid belt, scattered and thinned, a graveyard of rubble that once held the potential for planets. The Kuiper belt, a distant ring of ice, slowly sublimating into nothing as the faint heat of the white dwarf fails to reach it. And beyond that, the Oort cloud, that vast spherical shell of comets, a relic of the solar system's birth, will drift on, unchanged. It will outlast everything. Those comets, those icy orphans, will be the last witnesses to our sun's existence, carrying the chemical signature of our star for billions of years after it has gone dark. But even the Oort cloud will not last forever. The galaxy itself is a dynamic, chaotic place. The Sun, now a black dwarf, will continue its orbit around the centre of the Milky Way. And, over the eons, gravitational interactions with passing stars, with giant molecular clouds, with the galactic tide itself, will slowly strip away the comets. One by one they will be flung into the void, or pulled into other systems, or sent careening toward the galactic centre. The Oort cloud will dissolve. The solar system will become a single, solitary black dwarf, a lonely wanderer in an increasingly empty sea of stars. And this is where the story gets truly cosmic. Because the Milky Way itself will not last forever. In about 4 billion years, it will collide with the Andromeda galaxy. It will be a slow, majestic, violent dance of a trillion stars. The two galaxies will tear each other apart, their spiral arms unravelling, their gas clouds compressing into bursts of new star formation. The black dwarf that was our sun will be thrown into a new orbit, perhaps into the galactic halo, perhaps toward the core of the merged elliptical galaxy. It will be a refugee, a relic of a lost home, forever separated from the stars it once called neighbours. And even that is not the end. The universe is expanding, and it is accelerating. Galaxies will move away from each other until they are no longer visible. The cosmic microwave background will redshift into oblivion. The stars themselves will burn out. The last red dwarfs, the longest-lived stars in the universe, will finally fade after trillions of years. The universe will become a cold, dark, empty place, filled only with black holes, neutron stars, and white dwarfs. And then, even the black holes will evaporate, slowly, through Hawking radiation, over a timescale so vast that it defies comprehension. The last black hole, a supermassive one at the heart of a dead galaxy, will finally pop out of existence in a faint flash of gamma rays. And the universe will be empty. Truly, completely, eternally empty. But let me pause here, because I can feel the weight of this. It is easy to fall into despair when you look at the cosmic calendar. It is easy to feel that nothing matters when everything is destined for oblivion. But that is a misunderstanding of the cosmos. The universe does not ask for our permission to be beautiful. It does not demand that we find meaning in its vastness. It simply exists. And we are the ones who bring the meaning. We are the ones who look at a dying star and see a story. We are the ones who look at an empty universe and feel the ache of loss. That ache, that longing, that love for a world that will one day be gone, that is what makes us human. Think of the generations that came before us. The hunter-gatherers who looked up at the stars and told stories of gods and monsters. The ancient Greeks who measured the shadows to calculate the Earth's circumference. The Renaissance astronomers who turned telescopes to the heavens and discovered that we were not the centre of everything. The engineers who built the Voyager spacecraft, who sent a golden record into the void, carrying the sounds of whales and the music of Mozart, a message in a bottle for a universe that may never find it. They all knew, in their own way, that they were part of something larger. They all contributed to this moment, to this conversation, to this shared understanding that we are stardust, and we are temporary, and that is okay. And so, when you walk outside tonight, when you look up at the stars, remember this. You are looking at a snapshot of a universe that is constantly changing. The light from those stars has travelled for years, for centuries, for millennia, to reach your eyes. By the time it arrives, some of those stars may already be dead. But that does not make the light any less real. It does not make the moment any less precious. You are standing at the edge of time, connected to the cosmos by the very atoms in your body, and you are alive. Right now, in this brief, beautiful window of cosmic stability, you get to be. Here, do not waste it. Do not let the enormity of it all crush you. Let it lift you. Let it remind you that every sunrise is a gift. Every breath is a victory. Every connection you make with another human being is a defiance of the entropy that wants to tear everything apart. We are the universe's way of fighting back. We are the universe's way of saying, I am here and I will be remembered. And when the last star fades and the last black hole evaporates and the universe is nothing but a cold, dark void, there will be no one left to remember us. But that does not mean we never existed. It does not mean we never loved. It does not mean we never laughed or cried or dreamed. We did. And that is the most profound, beautiful truth of all. The cosmos does not need to remember us. We remember ourselves. And that is enough. This is the cosmic perspective. This is the gift of looking up. And I invite you, I urge you, to keep looking. Subscribe to This Is Space. Join us on this journey. Because the universe is vast, and it is magnificent, and it is calling to us. Let us answer.